Welcome to the continuation of the 2022 NASA STEM Enhancement in Earth Science High School Intern Science Symposium. SEAS is a collaboration between NASA, the University of Texas at Austin's Center for Space Research, and NASA Texas Space Grant Consortium. Former SEAS interns have gone on to major in STEM in college, interned at NASA centers and space contractors, and even been hired by NASA working on missions such as Europa. We are excited to learn about the future accomplishments of the interns from 2022. This year, we received almost 1,100 applications and selected 260 10th and 11th grade students as participants who were assigned to 18 different Earth and space science projects. Research was conducted in Earth and space science, environmental studies, climate research, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research in Earth and space science modules, Python coding, and project-specific work prior to starting their actual project tasks. Interns heard from 12 different NASA subject matter experts that highlighted NASA missions, opportunities, and careers during the course of this internship. You are in for a treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, the managers of the program, welcome to NASA SEAS 2022. Today, we have 13 team project video presentations. We will divide the afternoon into 3 sessions with 2 20-minute breaks, one at 2:10 and one at 3:40. Project video presentations will either be 5, 10, or 20 minutes in length, followed by Q&A. Please post your questions on the slido.com website and use the code SEAS2022. Here is our schedule for the day. We will have presentations by teams, followed by a 5-minute Q&A. We will invite each team presenting to turn on their cameras and their mics to answer the questions posed by those listening. During the 20-minute break, we invite you to watch the video highlights of the James Webb Telescope, as SEAS was selected as a first site, image site, along with highlights from SEAS alumni. Later in the day, we will be viewing highlights of the student intern produced products as part of the Earth and space science and Python projects. Our first presentations are by interns in the Galaxy Classification Group. Our Earth is just a small part of the whole universe. In addition to learning about the scale of the universe, students contributed to astronomy research through citizen science projects. While helping astronomers process vast amounts of data, students identified and classified galaxies. A special thanks to their project mentor, Dr. Judith Reese, for her commitment and dedication. Our first team presentation will be utilizing SuperWASP data on light curves to determine stellar classification and identifying black hole candidates. Please welcome the Black Hole Hunter team.
Welcome everyone to our presentation, Black Hole Hunters. This was a citizen science research project that we worked on as a part of the NASA SEAS internship.
Hi, my name is Miranda Blau, and I'm a rising senior at the North Carolina School of Science and Mathematics. I hope to attain a bachelor's degree in both geology and astrophysics with the goal of eventually conducting research with NASA in Antarctica.
Hi, my name is Isabel Levine, and I'm a rising senior at Sleepy Hollow High School in New York. I hope to pursue a career in aerospace engineering and mathematics with the goal of becoming an astronaut one day.
Hi, my name is Nicole Dang, and I'm a rising junior at Oakland High School from Northern Virginia. In the future, I plan on pursuing computer science and astrophysics, as well as studying their intersection.
Good afternoon, everyone. My name is Natalie Heschley, and I am a homeschooler from Brenham, Texas. After 12th grade next year, I hope to study astronomy in college, and my ultimate dream is to become an astronaut.
It is important to establish citizen science, which refers to a member of the public who volunteers to partake in scientific research. However, we decided that we can learn more from data provided than just identifying black holes, and we wanted to make our own inferences from the SuperWASP data we were analyzing. So SuperWASP, or the Wide Angle Search for Planets, is a multinational consortium of multiple academic organizations. It is financially supported and operated by Warwick and Keele universities in the United Kingdom. It consists of 2 robotic observatories that run throughout the year, one in each hemisphere, being Spain and South Africa, which ensures that the data collection is continuous throughout the year and the seasons. So it uses transit photometry to hunt for exoplanets. However, this can also be used to find black holes, especially stellar black holes, as well as variable stars. So some of the data may, however, be unreliable due to noise. As each pixel is being read out by the computer, a few additional electrons are being lost or acquired randomly, causing the readout value to deviate a bit from the actual collected signal rate, which creates unreadable data when the object is especially faint. So there are 2 primary compact objects, black holes and neutron stars. Although in this presentation, all compact objects we will be referring to, however, will be in reference to black holes. Black holes are extremely massive and dense celestial bodies, and they are formed when a massive star collapses onto itself. And by massive, we mean greater than 8 solar masses because of its immense gravity. So most stars exist in binary or triple systems. So if one star dies, the 2 entities will continue to orbit each other until the gravity draws them in closer and closer to one another. So the separation distance gradually decreases over the course of millions of years. Subsequently, the black hole accretes its neighbor's matter. And these systems in this phase are especially hard to find because they occur for a relatively brief period of the system's lives. Although, as I stated earlier, they can be up to millions of years. Additionally, these stellar black holes we are looking for do not emit X-rays, as the components are extremely far apart, making them findable only through alternative methods, such as lensing, which we will get into. Why do we use lensing techniques? These special binary systems make it possible to detect black holes because of this phenomenon called self-lensing. Self-lensing occurs when an orbiting black hole transits or passes in front of its companion star. So because of this, a black hole, as I said, is incredibly dense and heavy. So the bending of space-time due to the gravity around the black hole essentially acts as a lens which magnifies the light of the star behind it, making it appear extremely bright, as you can see in this graph in front of you. So the light curves show to be symmetric, a peak in the otherwise stable brightness of the star. Although astronomers believe that there are numerous black holes within the Milky Way galaxy, observing a self-lensing event like this is extremely rare because these transits occur once every few decades. This is the anatomy of a light curve. The graph presented here is an eclipsing binary light curve, and as you can imagine, this is very similar to some of the readable light curves we observed in Zoo versus Platform, where the x-axis is listed in the number of days, while the y-axis displays brightness or magnitude. From here, we use properties of a graph, such as the period, differences in maximums and minimum magnitudes, and a shape to make inferences about the celestial bodies that we were dealing with. So amid the thousands of pieces of data we looked through, we noticed that some graphs displayed repeated patterns which were not classifiable as black holes. After beginning to catalog some of these graphs out of curiosity, we realized that they were in fact akin to the distinctive light curves emitted by variable stars. As you can see here are some of the types of variable stars that we cross-compared with our graphs, including intrinsic stars such as rotational variables and eclipsing binaries, as well as intrinsic stars such as RR Lyrae, Cepheids, LPV, and Delta Scuti.
This is our methodology. To begin analyzing the citizen science data, the team underwent training to learn what characteristics the light curve of a black hole candidate would have. After training, we sorted through both simulated and real data, racking up a total of 6,710 total light curves by the end of the analysis. While looking through the data, the team looked out for both black hole candidates along with graphs that resemble variable star light curves. By looking for both, we were able to contribute to a variable star research by classifying as many different objects as we could. Then, from each real light curve that resembled either a black hole candidate or a variable star, we extracted the subject ID, right ascension, and declination and input them into a Google Sheet. After inputting the data into a Google Sheet, each light curve was classified into its most probable type as a variable star. The options that were decided on were black hole candidates, eclipsing binaries, rotating stars, RR Lyrae, Cepheids, and flares. However, we found no RR Lyrae stars. RR Lyrae stars and Cepheids are types of pulsating stars. Our primary goal was to look for black hole candidates, one of which is shown in this picture. A black hole candidate is set apart by an obvious sharp and symmetrical peak in the graph. One type of variable star classified was the eclipsing binary. Eclipsing binary graphs typically have rounded tops and sharper valleys in between, and periods less than 3 days. The next is a rotational variable star, which was the most populous in the data. Rotational variable stars have small amplitudes, symmetric up and downs, periods up to 100 days, and typically a lot of noise. The next light curve depicts a Cepheid, which has periods up to 80 days, larger amplitudes in rotational stars, and a steep ascending branch followed by a shallower descending branch, or vice versa. It is less symmetrical from the others, which sets it apart. Long period variable stars are similar to rotating stars, but have much larger amplitudes and periods ranging from 80 to 1,000 days. They appear sinusoidal and are symmetrical. Flares were identified by light curves with more than one peak. They resemble black hole candidates, but have multiple peaks with different heights, which repeat more or less evenly spaced. As I previously mentioned, we looked for but never identified RR Lyrae. RR Lyrae light curves resemble the shape of a Cepheid light curve, except they have a period of only a day or less. After each of the 400 objects were identified as some kind of variable, they were classified again by a different person without seeing the first classification to avoid bias. If the classifications matched, that became our official designation of the graph. If the classifications did not match, the group discussed the light curve together and consulted our mentor to verify our final decision. After classifying each star, we checked the SIMBAD astronomical database to see whether any of the stars were already classified and which stars we had classified for the first time. Even if the stars had been classified in SIMBAD, their classification was often broad, such as variable star or high proper motion star, which allowed an opportunity for us to classify it further.
Now I'll explain our research findings. Over the course of the 2-week on-site internship, our team conducted 6,710 citizen science classifications through the Black Hole Hunters project on Zooniverse. We identified that 358, which amounts to 5.5% of our total, were pulsating variable stars that have not yet been identified or classified as such. As of 2022, there have been approximately 150,000 of these classifications completed. In total, our team contributed to 0.25% of all pulsating variable star classifications. First, I'll present our broadest classification, intrinsic versus extrinsic variable stars. Out of the 358 new classifications, the majority, 89.1%, are extrinsic variable stars, while 10.9% are classified as intrinsic variable stars. For our more specific classifications, we observed that 81.56% are rotational variables, 8.38% are Cepheid types, 7.26% are eclipsing binary stars, 2.51% are long period variables, and 0.28% are flares. As seen by the graphs and statistics, the most common type of pulsating variable star that we found were rotational variable stars. Now we'll take a look at the star type breakdowns from the SIMVAD database. Within the 358 identifications, 66.9% are labeled as unclassified stars. 22.2% are high proper motion stars. 4.3% are decided as double or multiple stars. 1.6% are RS Canum Venaticorum variable stars. 1.4% are variable stars. An additional 3.5% are less commonly labeled stars, such as irregular variable star or post-AGB stars. Through this, we can see that the majority of the stars we investigated are completely unclassified. Additionally, we also identified 11 potential black hole candidates. This is one example. Here, you can see a stable and consistent path of points leading up to an abrupt peak, showing potential for a black hole. This is another example. Similarly, there is a clear peak that stands out among the data points. Overall, 0.16% of our citizen science classifications are black hole candidates.
In conclusion, we met the goal for our project because we successfully identified black hole candidates, logged newly classified variables, and grouped them into their specific classifications by using light curves observed by SuperWASP. To summarize our results, we sorted through 6,710 observations on the SuperWASP database and identified 358 of them as new variable stars. Within these classifications, which comprised 5.5% of all our data, we calculated that 7.25% are eclipsing binaries, 8.38% are Cepheids, 81.56% are rotational variables, 2.51% are long period variables, and 0.28% are flaring stars. In all, we helped to classify approximately 0.25% of all the currently known variable stars. Furthermore, based on the number of black hole candidates that we found, we calculated that the approximate probability of finding a black hole through Zooniverse is 0.16%. Overall, through our research, we were able to extend this project beyond just black holes to also considering the existence of pulsating variable stars and classifying them into their respective types. Despite all of the successes of our research, like anyone, we had to work around limitations to our project and the inherent errors within it. A possible source of error arose from the fact that the y-axis scales in the SuperWASP graphs are in brightness, but the reference graphs we used for classification are in magnitude. This difference in units caused problems for us because a variable's amplitude is one of its defining characteristics. If the difference between these units is great enough, potential differences between the graph shapes could have misled us to classify some stars incorrectly. Finally, the domains of the x-axis limited the amount of data for each of the curves that we could observe, so we may have been missing the full picture for some of the graphs. This means that we might have classified some variables incorrectly because we couldn't see the whole pattern of the data. Because our time at SEAS was limited, we were not able to complete everything that we originally planned, but going forward, there are several possibilities to improve our results and further our research. One way in which we could do this would be to expand our data set size to increase the accuracy of our classifications. Another improvement we have already started pursuing is to check our classifications with professionals. And finally, one interesting twist to our project could be to calculate the lifespans and masses of our stars in order to predict whether they are currently black holes. All of the light from objects that reach Earth took time to travel through space. So the farther a star is from us, the farther in the past we are actually observing it.
SEAS was one of the most enlightening experiences of my life. Prior to enrolling in this program, I knew that I wanted to work at NASA. Although I had been under the impression that much of what they did was limited to astrophysics. Visiting Johnson Space Center, however, taught me otherwise. It enabled me to see the variety of people that were, quote unquote, working behind the scenes. And these people are actively contributing to the study of space. So it essentially allowed me to explore a field that I had never even thought about before, which was geology. I had always enjoyed traveling, so learning that analog expeditions were popular in this type of research and would simultaneously allow me to conduct research with tangible objects that I can physically work with really struck me. So personally, I believe that this is one of the most impactful experiences of my internship. It really helped me solidify the vocational path I really want to pursue in the future. Pursuing that alongside astrophysics is something that I'm really excited to do. In addition, being able to work with my ambitious peers proved to be an invaluable experience for me, as it allowed me to meet like-minded people and develop my teamwork skills. Through working in the field, I got to learn more about topics like aerospace engineering, physics, and mathematics in ways which were relevant to my research, thus allowing me to grasp onto the information and learn how to apply it in an appropriate setting.
This was actually my second summer in SEAS. Since I was virtual last year, I was given the opportunity to apply again this year to be on site. I'm so glad I was selected to come on site so I can experience what SEAS was like in person and work closer with my group. It was a completely different experience, one that allowed me to become much closer to my teammates, listen to speaker series surrounded by other people, and participate in hands-on STEM activities. The biggest difference for me this year was visiting the Johnson Space Center, especially surrounded by people that share the same interests as me, because we got to explore and became so much more invested in what we were already interested in and hoping to pursue. Due to my time in SEAS, I became sure that I wanted a career working in STEM and one that allowed me to work with teams. I'm extremely grateful for the opportunities NASA SEA has offered me over the past 2 years and the people it has introduced me to.
SEAS is one of the most unique experiences I've been through. It was a great mix of engaging STEM activities, in-depth research, and group connection. This program has allowed me to grow in many different ways. As a student, I've been able to broaden my experience with astronomy, and SEAS has inspired me to continue pursuing a career in the field. As simply an individual, SEAS has allowed me to connect with a group of like-minded people who have made this program extremely rewarding and memorable. It has also challenged me to go outside of my comfort zone and get a sense of how it will feel to work in the real world and become independent after graduating high school. My favorite part about SEAS was being around my extremely goal-driven peers and mentors, as seeing them work hard motivates me to become even more focused on my own aspirations. I'm extremely grateful for the SEAS experience and would love to participate in similar programs in the future.
When I look back over the past 2 weeks, I still can't believe that I was blessed with this opportunity to engage in the SEAS internship because it all seemed too good to be true. This experience greatly exceeded my expectations, and I enjoyed all of the team building activities, the various field trips, and the amazing research opportunities. I was also thrilled to get a taste of college astronomy through this project, and it inspired me to continue pursuing a lifetime of learning more about the beauty, order, and truth in the universe. Overall, I am very appreciative to all of my teammates for all of their great ideas, hard work, and effective collaboration that made this project a success. And I am forever grateful for my amazing experiences and new friends. To conclude, we would like to thank NASA, SEAS, the Texas Space Grant Consortium, the Center for Space Research, and Zooniverse for making this amazing opportunity possible. Also, we want to thank Mrs. Baggio and Ms. Miller, who both put forth so much effort into this internship over the past several months. Last, but certainly not least, we would love to thank our mentor, Dr. Reese, for dedicating her time, thought, and effort toward assisting us with our project to help make it a success. Finally, here is a list of the sources we used for our project.
Thank you for listening.
Great job. So we want to invite the Black Hole Hunter team to please turn on their cameras and to unmute their mics. We have several questions for your team. So our first question is, What was the most difficult part of your research?
So I can cover this one. I would say the most difficult part of our research was the fact that the x-axes of the graphs we were analyzing, the domains of them were limited. So we couldn't truly tell if we were seeing the whole picture for a certain graph, which limited how we could see the periods of the graph in time. So that may have led us to incorrectly classify some stars. So working around that was probably one of the biggest challenges.
Great. So what is the difference between an intrinsic and extrinsic star?
Okay, I can take that one. So basically, intrinsic variable stars are stars whose luminosity physically changes due to pulsations, eruptions, or through swelling and shrinking. And on the other hand, extrinsic variable stars are stars that change in brightness because of being eclipsed or by stellar rotation or by another planet or star.
And the next question is, how much practice did it take for you to gain confidence in your star classification?
I can take this one. So classifying the stars correctly definitely took a lot of patience and a lot of teamwork because there are a lot of different types of stars and extrinsic versus intrinsic. So it took about, I would say, like 5 or so classifications for me to become comfortable, but I like constantly verified with my team even after I did like hundreds of classifications. So it was really important to just like all talk about it together in order to be like the most sure of what we were choosing.
So originally your team was the black hole hunters, but how did you come up with the idea for classifying variable stars in addition to black holes?
I can take this one. So basically, yes, as the question mentioned, we were originally going to only look for potential black hole candidates through the Black Hole Hunters Citizen Science Project on Zooniverse. However, as we sifted through our classifications, we noticed that we were seeing a lot of graphs with pulsating stars, stars that display variations of brightness. And because of this, we saw a potential for an extension of our project and decided to challenge ourselves to go beyond the original project goals. And as a result, while we were still searching for these extremely rare and hard to find black hole candidates, we were also simultaneously keeping track of the pulsating light curves we saw and classifying them.
And did the SIMBAD database allow you to match up stars and potential black holes?
So the SIMBAD database, for each coordinate point, it gave us like either that it was classified as like a general star, that it had been discovered but they didn't know what type, that it was like a variable star, and very rarely it told us more specifically that it was like a long period variable. But it never directly told us that it was a black hole candidate. It just told us normally that it was a variable star and like exhibited some form of like an and like a interesting graph that had to be examined more.
And why do you feel it is important to hunt for black holes?
I can take this one. So the importance of hunting for black holes is mostly to just expand our knowledge of the universe. And black holes are very interesting and exotic forms of matter and celestial bodies. So they can greatly help us understand more about the distribution of the universe. And it also, through the Black Hole Hunters Project in SuperWASP, it helps engage the public in pursuing scientific discoveries, which is really exciting.
And do you find a particular explanation for the trends that you observed while you were doing your classifications?
So one of the biggest trends we found was that there were a lot of rotational variable stars, and that was like an overwhelming amount. And then we explained this mostly by those graphs seem to be like the easiest to classify and the most popular type of star. So we kept finding that same pattern, and we just kept classifying it as rotational. So it's really just because those are just like the most populous in the sky.
And what would you say was your favorite part of this project?
So for me, the favorite part of this project was just being a part of this citizen science project and helping to contribute to search for these black holes and making an impact, basically. So like on this like big project, I believe that citizen science has helped a lot. It has helped scientists to quickly classify these black holes and find them.
Great. Well, you all did an amazing job. I congratulate you on your research and appreciate your contribution today.
Thank you.
You're
Thank
welcome.
you.
The next group in galaxy classification studied supermassive black holes, an exploration of galactic nuclei and jets via radio transmit emissions. Please welcome the team studying supermassive black holes.
Hi, my name is Ambika Grover, and I'm a rising senior from Greenwich High School in Connecticut. I hope to pursue a career at the intersection of the sciences and humanities in the future.
Hi, my name is Sarah Pinto, and I'm a rising junior at Barrington High School in Barrington, Illinois. I hope to pursue a career in astrophysics and eventually become an astronaut.
Hi, my name is Cynthia Routh, and I'm a rising junior from Ronald Reagan High School in San Antonio, Texas. I aspire to become an astrophysicist and astronaut, future Martian, when I grow up.
Hello, I'm Maliti Selakapu. I'm a rising senior from University Hills Secondary School in Vancouver, Canada. I hope to work in materials engineering in the future.
Hi, I'm Rashika Paranla, and I'm a rising junior at Capel High School in Capel, Texas. I aim to pursue astrophysics in the future and explore the field of relativity research. Let's get started by launching into space using our Athena-1 rocket. But in this adventure, we'll be going a lot further than just the moon, traveling well beyond the bounds of our solar system and galaxy, zooming out to examine extragalactic relationships.
In this presentation, we'll be taken on a journey through supermassive black holes, which are black holes a million to billion times the mass of our sun. As we head through the asteroid belt in the Milky Way, let's describe our final destination. Our project focuses on finding parts of galaxies you can't always detect using visible light, like the emitted jets of matter and energy that surround supermassive black holes, in addition to measuring the comparative ratios of the active galactic nuclei and their corresponding jet length.
These black holes are found to be in the center of almost every known spiral galaxy and giant elliptical, boasting a tremendous gravitational field which causes the formation of accretion disks, inward spiraling dust and gas. Jets of plasma occur when magnetic fields collapse and particles within the accretion disk are propelled into jets. We find that the major problem with the existing study of supermassive black holes is that the relationship between the size of both the galactic center and the jets is not often explicitly analyzed and described. This issue remains prevalent because many radio images that are available to the public contain these imaging inconsistencies that can affect future conclusions.
We aim to counter this issue by investigating 1,000 galaxies using the Radio Galaxy Zoo LOFAR software, the basis of citizen science, and use the collected data and images to answer fundamental questions. Specifically, does the given image contain an active galactic nuclei and jets that would be indicative of a galaxy? Beyond this, however, our group stepped beyond citizen science to complete our own investigations, as we'll highlight later in the presentation.
It quickly became apparent that the results of our preliminary classification differed from our expectations. We anticipated that a significant portion of the galaxies that were presented to us in the citizen science platform to be already highly accurate or classified by other people, since machine learning was already able to automatically group sources via solid blue ellipses. Instead, we were involved in classifying potential supermassive black holes that no one had looked at before. As we'll highlight in just a moment, the software was relatively inaccurate, which is the reason why human analysis is so necessary. We just passed through our Milky Way galaxy. From a distance, it looks a lot like our neighbor Andromeda, but let's take a closer look and zoom into its central black hole. Using public data known as citizen science, our project focuses on these black holes to accomplish goals we set up before we started our classification process. Here on Earth, a telescope called LOFAR focuses on these supermassive black holes and the radio signals we receive from the jets of the active galactic nuclei, which are supermassive black holes emitting jets of radiation and winds. LOFAR has multiple stations located across the Netherlands and Europe and has two types of antennas, low and high bands with a range of below 80 megahertz and above 110 megahertz. We can't detect any sources between these 2 points as that is the FM radio band.
Let's get a bit close to this black hole and delve more into the process our group took to break down this task into manageable pieces. Our methodology was based on the idea of cross-examining telescopic archives and analyzing prior research papers. Each member of our team followed a certain order of steps to ensure that we would yield consistent results, which we examined later when the research was done, with each individual classification taking up to 5 minutes.
First, we examined the project information given on the Zooniverse website and kept track of any important notes and/or mentions. We then created individual Google Drive folders and subfolders for each member of the team, so that each of us can store pictures of each classification we complete, along with categorizing it as a potential measurement source. Once the grouping had been completed, we then further grouped our sources into one we could actually examine by having a visible optical point of origin.
Now, using these optical options, members used Adobe Illustrator, the Sloan and Sinbad database, along with the celestial coordinates of said astronomical object to pinpoint its location in the night sky, and overlaid the optical image with the radio sources from Citizen Science website at the same scale. We then converted the redshift to a distance using a cosmological calculator created by Ned Wright from UCLA. After that, using the overlaid image, we will measure each jet and the AGN, getting a ratio as a result, later analyzing our findings as a group. This process was extremely important in maintaining our organization and efficacy as we manage hundreds of data points.
In order to help astronomers detect supermassive black holes, we needed to analyze background images via optical telescopes and radio emissions, shown in yellow contour lines. Our interface also has one or more light blue ellipses, where the solid line is the target and the dashed line or lines are nearby radio sources, which might or might not be related to the targets. These areas that the computer believes to be separate sources, but it sometimes makes mistakes in identifying the products of the optical source. We analyzed about 1,000 images by noting which radio contours are emissions of the source, via placing a mark in certain dashed ellipses, and which optical object is the source of the radio jets. We also came across situations where the ellipses weren't related to the optical source in any way, or the image itself could have an error, or a special case where it is hard to make any conclusion. From there, we were able to further classify the type of galaxy we were looking at. We specifically aimed to determine if these were double or single-lobed radio sources. We were able to also detect various anomalies or special cases as we previously mentioned. The most notable were as followed. First were artifacts where the radio sources are distorted due to calibration problems. This happens when a bright radio source is close by, therefore possessing a sort of explosion-like effect. The second scenario is when something was too zoomed in, where radio regions go far beyond the borders of an image. Basically, we can't tell what we're really looking at. The third scenario is with blends, where the blue ellipse, as we've shown previously, views two or more separate sources and groups them together when they should be separate. But the last scenario is on diffuse radio sources, where the image doesn't actually map any radio structures to begin with. We then examined the radio sources to see if the contour lines surround any visible optical source. After we finished analyzing each source, we noted its information on the spreadsheet with its name, position, whether or not it had jets, and what kind of source it was. We then created and placed each image into its designated folder and created charts to see what kind of sources we encountered throughout this entire classification stage.
As the graph illustrates, we discovered a diverse set of galaxies in which 21.6% turned out to be artifacts or otherwise uninterpretable. 21.1% were too zoomed in to view the whole galaxy. 13.6% were blends in which there were several indistinguishable sources. 12.7% had multiple sources. 9.9% had faint optical sources. 9.6% had radio signature errors. 6.5% had double lobes. 4.6% had asymmetric jets, and 1.5% had no jets. These results were surprising. Only about 11% of the total galaxies classified yielded genuine supermassive black holes with clear optical sources.
As an element of our further research to answer our developing inquiries, we also thought it would be interesting if we calculated the distance to each source. To do this, we used an archive called the Simbad Astronomical Database, and using a coordinate query, found the redshift of said object. Once we had the redshift, we calculated the linear distance in megaparsecs, using a cosmological calculator, given the Hubble constant, a factor that tells us how fast the universe is expanding, in this case, 69.6, redshift Z from Simbad, and omega matter and vacuum, 0.286 and 0.714 respectively. However, while the essential parts of our project had been accomplished, we still had our own questions to answer, particularly the ratio of the jets to the active galactic nucleus.
From our earlier classification and procedure stage, we mentioned how we organized our source images into subfolders. One of those folders, called subgroups for measurements, were images that had undetectable radio jets. From that folder, we filtered out the images that had bright optical AGNs called ratio options, and we had 23 of them at the end, with our original goal of having 20.
Once we had our images, we used a Sloan digital sky survey to match our sources to known objects in the sky. Then, after taking a screenshot of the sky from that website, we used Adobe Illustrator to overlay the citizen science and Sloan images, essentially matching up the sources to one another, so we could see the jets at the same scale. We did this to visualize how the jets are scaled relative to the actual image being taken by Sloan.
Point of interest and concern during this process was that of consistency, specifically between the 5 different individuals. The reason why citizen science exists is because machine learning has its limitations. That is, it can determine potential radio sources and group them loosely together in areas bounded by these blue solid ellipses, but it's really unable to determine if they're jets, stars, artifacts, or others. Of the 1,000 galaxies classified, roughly 44 of them were analyzed by 2 or more group members, and on occasion, the algorithm would cycle it through so that we would classify and make another classification on the galaxy more than once individually. As the graph illustrates, we analytically determined our success rate to be about 90.7% in terms of having consistency when multiple group members analyzed it. This made our group's collective accuracy nearly 15 times more accurate than the best standard machine learning tool used in LOFAR, and provides information that is incredibly useful for scientists operating the Galaxy Classification Citizen Science Project.
Our goal in the next step of the process was to find the ratio of the length of the jet to that of the AGN, which we measured in centimeters to 2 significant digits. We took measurements of the length of each jet, measuring variables J1 and J2, the radius of the active nuclei, variable R, and took the average of the 2 jets. Note that we measured each jet from the farthest end to the innermost radio source to the farthest end of the AGN, not necessarily from one end of radio emission to the other.
Once we got our measurements, we calculated the ratios between the radius of the optical source and the distance between the source and the end of the jets. Typically, there are 2 jets per optical source, so we would average the distance between the 2 jets to calculate the relationship with the radius of the source. Looking at our measurements, we can see that there is a positive linear relationship between the radius of the source and your distance from the source to each of the jets, which we expected from the start of the project. As the radius increases, the length of the jets also increases. A larger active galactic nucleus radius indicates a brighter optical center, and a brighter optical center means more energy emitted from the jets.
It was at this stage of analyzing at the end of our research that we had began to reflect the entire process. As a group, we encountered many challenges that at the time hindered our ability to proceed with the rest of our research. For example, the Sloan database had difficulty showing us a scale in arcseconds in order for us to make an accurate measurement of the jets. As a result, we had no way of accurately determining the linear size of the jets and the active galactic nucleus, but we resolved to physically gauging the distance using centimeters and calculating the ratios from there. In addition, finding an appropriate website to display the scale of the images proved to be difficult, but we eventually came across the Sloan and Simbad database suggested by our mentor. And lastly, we considered a relationship between the angular velocity of objects orbiting in the accretion disk and the energy emitted by the radio waves. However, we realized that it would be too difficult to determine the angular velocity due to its non-uniform nature.
Through our research, we furthered the scientific disciplines surrounding supermassive black holes, active galactic nuclei, and jets through 2 primary objectives. First, we contributed around 1,000 classifications to existing scientific efforts, helping scientists as they work to identify these supermassive black holes as part of their careers, and offering support for efforts such as the LOFAR Galaxy Classification Citizen Science Project.
But secondly, our efforts extended far beyond just classifying galaxies and helping out scientists. Our group took a novel approach at examining the relationship between the relative size of radio jets of an optical source and comparing it with the breadth of jets. We were able to successfully establish a relationship which has the potential to help scientists learn more from the jets of galaxies that we can see, and even if the optical sources are not visible in those instances.
Overall, this research project was truly exciting and challenging. We wouldn't have had this opportunity if it weren't for Miss Margaret Baggio and Miss Selena Miller, including everyone from SEAS, for creating an opportunity and environment that challenges us yet motivates us to pursue our goals, research and career-wise. On behalf of all of us, we want to express our deep gratitude and appreciation for Dr. Reese for her support, enthusiasm, and patience while working for us on our project. Thank you, Dr. Reese.
Finally, we want to extend our thanks to the University of Texas at Austin, the Center for Space Research, the Texas Space Grant Consortium, and NASA for giving us a chance to explore our passions and interests. SEAS meant so much to each one of us, but as we reach the end of our presentation, we would like to discuss our favorite moments from our internship and how it impacted us. When my group and I were talking about our favorite part of SEAS, the first thing that came to mind was the amazing people I met. Whenever I came across one of our challenges, I could always depend on my teammates to get to the solution. My teammates and I also grew very close with one another over the duration of this internship. I'm so grateful that I got this chance to meet them. My favorite moment of the whole experience was going to see the astronaut training facility at the Johnson Space Center, and my team and I researching and playing card games in the study lounge. SEAS motivated me to pursue my dreams of becoming an astronaut and going to Mars one day. It made me confident in my abilities, yet humble with accepting critiques.
SEAS was such a valuable experience that I honestly would have never dreamed of taking part in. It's honestly too difficult for me to put into words just how much SEAS meant to me, and I'll never forget all those late nights researching, thinking we made a breakthrough, and getting closer with the team along the way.
SEAS expanded on a variety of unfamiliar topics, including blackbody radiation and particle collisions throughout our research. I loved how in SEAS I was able to visit multiple places as part of our learning, but my favorite location was Johnson Space Center, where we were immersed into Artemis exhibits, which were incredibly inspiring to me. I often had to apply my physics and astronomy knowledge during SEAS, which solidified my liking for astrophysics as my career path, in addition to improving my collaboration, scientific research, and problem-solving skills.
Both in and out of our mentorship time, SEAS was an incredible opportunity to learn about all that NASA does. I quickly learned that there are endless possibilities in terms of what we're able to pursue in the future, from being a scientist working at the International Space Station, a doctor exploring the effects of space radiation, or leading the way out on mission control. SEAS truly opened up a world of possibilities that I hope to find myself involved in the future, one way or the other. It's also been incredibly inspiring to see SEAS alumni explore these diverse fields later in their careers.
SEAS was an incredible experience for me, not only because of the knowledge I gained, but also because of the people I met. Being able to get research experience in a science field I wish to pursue at such a young age has been an amazing opportunity for me to solidify my career aspirations. My favorite part of this program was visiting the astronaut training facilities at Johnson Space Center, which was very inspiring to see. Overall, participating in the SEAS program has led me to develop confidence and teamworking skills while having fun working on something I'm passionate about. We are now returning back to Earth after exploring an active black hole. Thank you so much for listening, and we're happy to answer any questions you may have.
Excellent work. So I want to invite everyone on the team to please turn on their cameras and unmute their mics. We have several questions for you. And the first question is, why don't accretion disks get sucked into their black holes?
So I can take this question. Basically, you have to be on a direct collision course with a black hole in order to get sucked into one. So unless you were directly on the event horizon of a black hole, which is basically their border, you wouldn't get absorbed. In terms of the accretion disk, the angular momentum that the dust and gas have when they're spiraling around a black hole, it's too great for them to be immediately absorbed into the black hole. And there's also an occurrence called viscosity within the gas of those particles, where the outer rings of the orbit prevent the inner lines of dust and gas from slowing down and going directly into the black hole. But there is an inward spiraling effect that does take place.
So why don't you think machine learning performs, or how do you think machine learning performs in classification of black holes? And do you have suggestions for improvement?
Yeah, so this question was certainly something we noticed very early on in the process. So the way citizen science operates, as we mentioned in our presentation, is that it initially basically groups radio sources together. And that's basically the extent to which machine learning operates. So we are able to see general snapshots of the sky where there's lots of radio sources. But the issue comes into play when we're actually trying to figure out what supermassive black holes look like. And it's something we described in our presentation is how there are so many different types. Like we can have artifacts which look like almost an explosion of radio sources on the screen. But what we were looking for is these clear, distinguished jets coming out of a centralized source. And that sort of thing is something machine learning has been really limited in doing because there's not like one way that it can appear. So we can have jets that seem like they're coming straight out of opposite ends of the galaxy, or they can be seem like they're wrapping around something or reaching for each other. And those sorts of variables make it very difficult. So with that said, I think that training machine learning going forward, and this isn't something we can necessarily do right away, but certainly using data sets that train on these variety of supermassive black holes that we have been able to classify, which is something that citizen science is actually doing, that would certainly be a possibility to help us improve machine learning in a way that results or relies less on humans to actually do these classifications themselves.
Great. And how do supermassive black holes die? Is it similar to the way a star dies?
So I can begin the answer to this question. Black holes basically evaporate in a process called Hawking radiation, which was discovered by Stephen Hawking, in which the black hole loses energy through particle divergences that occur at its event horizon. And as the pace of these divergences quicken, the black hole gradually condenses and becomes smaller. And with that, the radiation that it emits becomes larger and larger until it experiences a large explosion, which is equivalent to the energy emitted by like simultaneous nuclear bombs.
And I can take the rest of this question. So as Rich said, the black hole sheds its mass through this energy called Hawking radiation. And as for how long this process takes, it generally depends on what kind of black hole you have, because you have stellar black holes, you have supermassive black holes, and depending on the mass, it takes longer. And it takes a really long time, almost like 10 to the 100th, so like a Google amount of years. So this process, it's really slow in a way, and it takes almost forever to complete.
So did any of you have a favorite galaxy that you classified?
So I wouldn't say the way we kind of did this is that we didn't actually get the names of the galaxies we were classifying. But with that said, we did have some pretty cool ones that we got to look at. I think some of the ones that were always the most interesting and almost were like a puzzle in the way we solved them is when we had two jets sort of like reaching towards each other, but we couldn't see the optical source. So basically there was something that was meaning that we couldn't really see the original place at which those jets were coming out from. So we didn't really have, a specific name for a galaxy, but I think those are really fun to, turn the computer around and have everyone huddle around and, try to figure out what galaxy or if that was a supermassive black hole.
And as you worked through your project, did it change the way your view is on how we should study the universe?
So I think that doing this project made me realize how simple doing amateur research on studying the universe really is, because through this project we used a lot of free and very accessible online databases like Sloan, Sinbad, and then of course the Citizen Science website, which are completely open to the public. So I feel like doing this research on celestial bodies and the study of the universe has never been so easy, and it made me realize how accessible it is just to anyone who is wanting to do that research.
Excellent. Well, you have all done an amazing job with your research, and thank you for joining us today to share your results. So we will continue our team presentations from the Galaxy Classification Group. The next presentation is analyzing properties of nearby and distant galaxies through the HETDEX Citizen Science Project.
Hello, my name is Michelle Adkala. I am from Brownsville, Texas, and a rising senior in LFHS. In the future, I plan to pursue aerospace engineering and astrophysics.
Hi, my name is Angel Hu, and I'm a rising junior at Central Magnet School in Murfreesboro, Tennessee, and I would like to pursue a career in physics or astronomy.
Hello, my name is Gauri Nanda, and I am from Frisco, Texas. I'm currently a rising senior at the Texas Academy of Mathematics and Science, and I aspire to study computer science and astrophysics in college.
Together, we are in the group Galaxy Classification and the subgroup Dark Energy Explorers. For our project, we separated nearby and distant galaxies using HETDEX Citizen Science data. For our outline, we'll be discussing the context of this entire project and the process in which we collected our data. The universe is expanding, we know that already, but upon a second shock starting in the late 1990s, when two teams gathered distances to high redshift supernovae, presented their data, we have learned that that expansion is actually speeding up.
As the universe expands, light from distant galaxies is stretched to longer wavelength, and this equation for redshift is essentially just the change in wavelength, where high energy light waves move down the electromagnetic spectrum to infrared light and takes a more red tone. Edwin Hubble explored redshift to identify the velocity of galaxies, and he deduced that they were moving away from the Milky Way. He came up with Hubble's constant, suggesting that the universe expands at the same rate in every location. However, Hubble's constant deviates from a linear relationship at high redshifts, and redshift and distance do not have the same relationship as previous models predicted. Using numbers from the Nedright cosmological calculator, we plotted two lines, one accounting for the mass density of dark energy and one ignoring the effects of dark energy. This produces a relationship that deviates at redshifts greater than 0.5. Thus, at higher redshifts, Hubble's constant does not hold true and the universe does not expand at a constant rate, possibly as a result of dark energy.
What is the cause of this? Astrophysicists determined this phenomenon to be dark energy, which is thought to be the acceleration of expansion when introduced by American cosmologist Michael Turner in 1998. The name has no correlation to what is involved, and the nature of this subject is still debatable. Whether dark energy is a cosmological constant or something that causes galaxies to be pushed away, we do not exactly know what it is yet. When exploring dark energy, we absolutely have to bring up dark matter and not get them confused. Dark energy is not the same as dark matter, but they both serve roles regarding the fates of the model of the universe. Dark matter makes up most of the mass of the galaxies and galaxy clusters, and it keeps them gravitationally bound together in a structure. They are assumed to be a mixture of dust and remnants of stars, planets, basically matter that does not emit light that is visible or infrared. Dark matter is probably a yet undiscovered particle, which does not emit any EM radiation. In the 1930s, dark matter was introduced by Fritz Zwicky through his calculations for the Coma cluster. These calculations contained errors that gave proof to the existence of dark matter. The reason being is that the cosmic cluster was rotating at such a speed that it could not hold its own structure. Therefore, there must have been matter that is not seen by the eye keeping it together. So the most exciting part of science is realizing we might have misunderstood absolutely everything, including the fundamentals. Should dark energy and dark matter actually exist, our interpreted composition of the universe is backwards, leaving observable luminous matter to be only 5%.
Thus, to contribute to the search and study of dark energy in the universe, we turn to classifying galaxies from the HETDEX Citizen Science Project. HETDEX, also known as the Hobby-Eberly Telescope Dark Energy Experiment, is a currently ongoing project at the University of Texas at Austin's McDonald Observatory that takes spectrograph images of many galaxies in the universe. The way this project works, is that it is able to collect data during clear nights in the sky. And also the main goal is to get the redshift, or eventually get the redshift of distant galaxies in order to create a 3D map of the universe to study how dark energy is able to cause the acceleration of the expansion of our universe. VIRUS, also known as the Visible Integral Field Replicable Unit spectrographs, is a tool that takes 150 spectras of the sky to create different images in different wavelengths. This is done to detect for different objects that might be detected in the sky. This tool is made to collect data from galaxies that are 9 to 11 billion light years away in order to create the final map and study the universe in a deeper way. So where does citizen science come in? So HECDEX needs to pick up only the distant galaxies from this huge set of observations. Instead of solely relying on scientists to just look at thousands of images from HECDEX, citizen science is able to allow normal citizens like you and me, just regular people, to contribute to such a big project by helping classify this data. While we can use artificial intelligence has many limitations. Humans are much better at differentiating and checking between what is a galaxy, what is not a galaxy, and being able to differentiate between a distant and a nearby galaxy. However, in order for the artificial intelligence algorithms to work, machine learning is required, and in order for machine learning to work, we need human input and human data to be able to make sure that that works correctly. Therefore, the Zooniverse Dark Energy Explorers project is a project that allows citizens to provide data for the machine learning, and this allows us to speed up the research on this project. And while it also allows citizens to participate in a STEM project and participate in research like this, it also educates the public on STEM, which is very exciting because this can foster and inspire many people to be excited about topics in STEM and potentially even pursue this kind of research in the future. So here's how we analyze the data. So what we wanted to do is we first wanted to look at different images and be able to figure out if it's a galaxy or not, or if it is nearby or far away. So first, as you can see, all of the spectra that we get from HECDEX comes in images that we have to process. As you can see in the throwback, you can see that in each of the colored boxes, which represents the area of focus in a different wavelength, you can see that there are no strong dots. So if you can see a black dot, that indicates that a photon of light is being detected. However, you do not see many black dots or clear black spots in the throwback image. So that means that this is clearly just noise. Additionally, we can also see that the curve does not fit very well. There are many outliers in the graph itself, and there's also no signature. If you can see a yellow dot in the signature, then that can indicate that there's an object being detected. However, we are unable to detect anything from that area. As well as in the main area of focus, we can see that around that area of focus, there are other objects as well. And so the area of the main focus in the red box does not really have anything that we can actually detect anything from. However, from the keep section, we can see that a dot appears in the focused areas in several different wavelengths, and the curve fits very well. Additionally, there is a very, very small and faint area for the object of focus to be focused on. And there's also a yellow dot that indicates that there is some kind of signature that is being detected. We can tell that the keep is a distant galaxy. Meanwhile, what we have to throw back is noise, which will not aid us in our research. So when we are analyzing the data, we need to check for clear points in all of the colored boxes, which will indicate that it is a galaxy. We also need to make sure that the spectral points, the blue dots with the error bars, are fitting with the curve. If it's a good fit, then it might be a galaxy or maybe another object. And if it's a bad fit, then it's noise that we don't really need. Therefore, human input is very necessary for precision and accuracy of making sure that all of this data is being processed correctly.
So what can the fit and the shape of the spectral lines tell us? Well, they can tell us the type of object, as black holes typically have flatter peaks, and stars and galaxies usually have longer spectral lines. They can also tell us about the composition, the wavelength of spectral lines in the full spectrum, which the database does not provide, can tell us what elements are present in the object. Redshift. Calculating the difference between the redshifted wavelength and the rest wavelength and dividing it by the rest wavelength gives the value for a redshift. Thus, the higher the redshift, the further the objects. And the database does not provide this data since we are picking galaxies for which redshift needs to be measured. And finally, nearby objects. Nearby objects caught in the image can affect the spectra, and phenomena such as galaxy mergers or collisions, star formations, supernovae, and black hole accretions often generate spectra with many peaks and valleys which may not appear to fit on the line. Part of the project is to separate nearby galaxies from distant galaxies. Nearby galaxies usually have a distinct shape in the signal, a clear black dot, and spectral lines with a very close fit. Distant galaxies, on the other hand, usually have fainter signals, which make the data points noisier and more scattered around the black line, appearing to be not as close of a fit. We can also classify different galaxies by using the images and the signals and the spectral lines. For example, spiral galaxies have distinct spiral arms in the image and very strong emission lines with a very high peak and a very close fit with a clear signal. Elliptical galaxies, on the other hand, are usually farther away with not as clean of a fit and many smaller peaks in the lines. Irregular galaxies are somewhere in between and do not have a distinct shape, but like the spiral, have very short lines and a high emission peak.
Other objects that we classified from HETDEX data include things like black holes. So as you can see, black holes are very strong, and you can see a very long dark streak appearing through different frequencies as well. And so this first image indicates that this is a black hole in a galaxy. You can also see that in the area of focus, you can definitely see that there's some kind of shape that indicates that the object that it is focusing on is a galaxy as well. The second image contains an asteroid. In the big image that you can see that there's a very long line going through the image. That indicates that there's an asteroid. An asteroid can provide some noise, so that is definitely something that we have to check for. However, in this image, we can also see that the asteroid is just a long dark streak in the full image, which is very cool. Finally, another type of image that we can see is a star. If you can see a lens flare kind of image appearing, that indicates that there's a star that is being detected as well, and also being shown in the images. While these cases are not distant galaxies or exactly galaxies, it is still very interesting to be able to tell and differentiate between different objects in space.
Now that we have gathered our data, we can now present our statistics with different focus. Our first set of statistics discusses whether our data was real or fake. In a total of 317 classifications we accumulated together, about 177 were real signals, and 140 were just noise, fake signals from the telescope, instruments, stuff like that. For our second set of statistics, we discuss if galaxies are nearby or distant. Our distant galaxies accumulated were 75, nearby was 73, noise was 139, and a new category of other being black holes, stars, and asteroids being flat 30. If you would notice here, noise once was 140, however now it is 139, specifically for these set of statistics. That being due to one of our data points fitting in a new category labeled other. Though it is still noise, it suits this category much better. And for our last set of statistics, we discussed the type of celestial objects that we viewed within these data sets. Of course, 148 were galaxies, our main area of interest. However, 24 were black holes. We found 5 stars and 1 asteroid.
Some of the potential personal challenges and also future issues with the Dark Energies Explorers. Some of the challenges and potential issues with the Dark Energy Explorers project includes a large amount of data, as not every observation is useful. As you can see with the statistics, there was a lot of noise and a lot of other objects that may not be able to help with us calculating the redshift. Additionally, there's no automated algorithm, which does require a lot of user observations to be able to complete. And for our own project and our own calculations, there was no right ascension and declination. Due to this being a citizen science project, we were not really able to access a lot of the specific details of many of the subjects and many of the galaxies that we classified. So finding the right ascension and the declination or the coordinates of the stars would have helped us to be able to actually find the redshift and make calculations. However, since those were not provided, we were unable to make many calculations.
So how will researchers at HEDEX use this information to gain more insight about dark energy? There are some calculations that can be made using the redshifts of distant galaxies. We could calculate their distances away from us and each other to create a map of the early universe. We can use baryonic acoustic oscillations to analyze the distribution of distant galaxies, which can tell us about the effect of dark energy on the early universe and provide insight to how the universe expanded and accelerated in the beginning.
So how can this help us in the search for dark energy? By aiding the process of clarifying data in the HEDEX project, we're able to proceed further in science as scientists can now focus on creating an accurate model of the universe with precise measurements. Essentially, we are the first step. We're the first step to solidifying distance of distant galaxies and their ages. In the end, this will let us know if dark energy is truly out there or if we have fully misunderstood gravity itself.
On all of us, SEAS has had a very big impact, from allowing us to learn about different topics in the space field, as well as letting us network with many mentors and many individuals in the industry, and as well as inspiring us to continue pursuing this topic. SEAS has definitely inspired us and has impacted our lives in many ways. And also, it was just a lot of fun.
For me, SEAS has allowed me to delve a lot deeper in the fields of astronomy and physics, and I am much more inspired to pursue a career or study those fields in college now. Additionally, I have had the opportunity to make many great friends and meet many like-minded individuals who have inspired me to keep on going with my research and not give up.
As someone who's interested mainly in aerospace engineering, I'd always focus on the mechanics and just building the rocket, building the satellite. But after working on projects such as these and being with other people who are like-minded, I've gained a new interest in astronomy, and I hope to use my aerospace engineering skills to, proceed in the science of astronomy, like making a telescope in that sense.
Personally, SEAS has impacted me a lot by allowing me to network and get to meet a lot of people in the industry as well. It was just so much fun to get to work with my mentor, and I also really loved getting to talk with a lot of NASA scientists and also with the speakers that have come during our internship. Definitely, I love astronomy and physics. However, it was just so much fun to actually get to work on a project involving those topics and even look into future applications for fields that I want to study, such as computer science and programming and other things in astrophysics as well. Definitely, this project was a lot of fun, and I'm very glad that I got to participate in SEAS. With all of that being said, we'd love to thank this program. We'd like to thank NASA and the Texas Space Grant Consortium, TSGC, for funding the SEAS program, and the Center of Space Research at the University of Texas at Austin for letting us use their facilities. We'd also love to thank Mrs. Selena Miller and Mrs. Margaret Baggio and all of the chaperones and people who have helped contribute to this program. We greatly appreciate your support and help in this project. Additionally, we would like to thank our wonderful mentor, Dr. Judith Ries, for guiding our project and giving us a lot of support in this field. We appreciate her very much. And a special thanks to Dr. Carl Gebhardt. Dr. Carl Gebhardt actually created the Dark Energies Explorers Citizen Science Survey, and he also presented to us about dark energy and black holes. Definitely check out the Dark Energy Explorers project on Zooniverse, and you can also classify galaxies yourself to contribute to this research project. With that being said, thank you very much for listening to our presentation. If you have any questions, please let us know. Thank you.
So I want to ask all of the team members to please turn on your cameras and unmute your mics. You have several questions. So the first question is, what is your opinion of the possibility that previous evidence of dark matter and dark energy could be attributed to our lack of understanding about gravity?
If I could take this one. So the question was about the understanding of gravity, correct?
Yes.
Okay, with that, well, personally, in my opinion, there's so many theories we have about dark energy and dark matter that I feel like, of course, our misunderstanding of basic physics and gravity is, of course, a huge possibility, as it is in science. Starting from the very beginning is something that is inevitable. However, there are also other theories on basically the material of the dark matter and the dark energy that even Neil Tyson has had ideas that stuff like dark energy and dark matter is actually from a multiverse, which is something we started exploring recently, that of course our dark matter is actually some other universe's ordinary matter. So there's so many possibilities and theories that I feel like our misunderstanding of gravity is not the only possibility there is.
Great. So the next question is, how did this project change your idea about dark energy?
I can take this question. And basically through this project, I came to realize how little we still know about dark energy, which is why this citizen science project exists, is to further the study of dark energy. While there has been proof that it does exist, we still don't know much of the details, like how the rate at which it's causing the universe to expand, which is what this project seeks to discover. And basically there's still so much to learn about dark energy.
What do the colors in the signature images represent?
I can take this one. So if you saw in each of the images that we were looking at, each different box was known as a fiber spectra. So since the hetex takes different images of the spectrographs, each colored box is technically meant to represent or meant to see a different part of the light spectrum. And so if you are able to see something appearing in multiple of those boxes, that means that there's probably an object that is there.
Great. And why do you think that galaxies were more frequent than stars or black holes in the data that you analyzed?
If that's okay, I think I could also take this question as well. So we looked at the main purpose of this project was to find galaxies. So we weren't mainly focusing on finding stars, and we were also mainly focusing on trying to find distant galaxies as well. And black holes are also pretty uncommon to be detected. They are there, but they're also pretty difficult to just find. And also for stars also just tend to kind of appear when we are making galaxy classifications as well. So we're just mainly looking for galaxies rather than stars or black holes or other objects. So that's why a lot of the classifications would have been galaxies.
Great. Well, you have all done a wonderful job with your research. Thank you for sharing with us today. We are ready to move on to the next group, the Using Satellites for Climate Disaster Preparedness team. They analyzed severe flooding, expansive wildfires, long-term drought, and extreme heat waves that worsened by ongoing climate change. In this project, interns examined natural disasters using real satellite data sets from NASA, the European Space Agency, and the U.S. Geological Survey. Students learned how to map, graph, and visualize climate disaster impacts while entering the world of geospatial and data science using QGIS and Google Earth engine applications and through coding with Python and JavaScript. A special thanks to their project mentor, Teresa Howard, for her guidance and dedication. So please welcome the Visualizing Climate Disaster Impacts on Texas and Australia team.
Hello, and welcome to the Sea Science Symposium. We are the Climate Disaster Preparedness team, and during our research internship, we worked on visualizing climate disaster impacts on Texas and Australia from 2000 to 2022 so that we can predict future disasters.
Hi, my name is Gia Gill. I'm from San Jose, California, and I'm interested in computer science.
Hi, I'm Helen Lee, and I'm from Swanee, Georgia, and I'm interested in earth and environmental sciences.
Hi, I'm Srimanura Simhan, and I'm from Seattle, Washington, and I'm interested in a career in computer and environmental sciences.
Hello, my name is Shruti Natala, and I'm from San Diego, California, and I'm interested in studying computer science.
Hey everyone, my name is Matthew Noriega. I'm from Houston, Texas, and I have an interest in statistics and business analytics.
Hi, my name is Ethan Palash. I'm from Austin, Texas, and I'm interested in computer engineering.
Hi, I'm Catherine Sullivan. I'm from Seattle, Washington, and I'm interested in computer science.
Hi, I'm Anita Thokadam. I'm from Plainsboro, New Jersey, and I'm interested in computer science and earth science.
Here's a quick overview of what we'll be going over in this presentation. Let's dive right in.
So what is remote sensing? Remote sensing is collecting data about our planet while observing it from space. While ground observations rely on human input and are limited in area, remote sensing allows for global coverage by observing from space. Passive satellites, such as the Landsat pictured in the right of this slide, detect the wavelength and magnitude of light waves emitted from the surface. Based on where the waves fall on the electromagnetic spectrum, conclusions can be drawn on the type of surface in that area. The satellites we use in our research are shown on this slide. We utilize a range of passive and active satellites in our research.
In order to map raw data accessed through Google Earth Engine, we utilize Python and Google Colab to access the datasets, stratify them, and display them in unique ways. First, we used a series of statements to import the datasets and create an image collection, which includes all points of data in a given date range. Then, we used a series of statements to reduce the collection by averaging images, selecting specific ones, or performing operations between two images to produce a product. Then, we defined parameters such as a color palette and numerical range and mapped the data. This is just the basic mapping process, but more complicated tasks were done in order to create time-lapse GIFs and integrate multiple datasets to create a risk map. In addition to mapping with GEE, we utilized libraries like Pandas to create time series graphs.
Let's talk about some of the ways that we utilize Google Earth Engine to conduct our research. This animation shows surface temperatures of the Pacific Ocean, as shared through the NOAA dataset with data collected by the Pathfinder satellite. It shows a natural circulation process called upwelling, which is where warm water is pushed aside by powerful winds, allowing cooler waters to circulate upwards. El Niño and La Niña are events that break this typical cycle. We map them in order to track their intensity and effect on precipitation and drought in the context of our target areas, Texas and Australia. These two maps represent the anomaly in ocean surface temperature leading to an El Niño or La Niña event. Each calculate an average of ocean surface temperature over 10 years leading to the event, and find the difference between that and the event year, forming a visual representation of the difference from average conditions. The map to the left shows the 2015 to 2016 El Niño, mapped by our group, with visible Pacific warming around the equator. The map on the right shows the intense 1998 to 1999 La Niña event, with clear surface cooling in the Pacific around the equator. The effects of El Niño and La Niña are significant across the continents adjacent to the Pacific Ocean and bring severe climate shifts like shown on the slide in North America. Currently, we are in a La Niña period in 2022 and 2023, and satellite data released in the near future can give insight to the severity of the event happening now and how it may affect the climate. The important thing to note is that El Niño and La Niña are the linking factor between climate changes in Texas and Australia, which are inversely related. Understanding how it affects each of these areas can enable us to make accurate assessments of risks such as wildfires and floods in a given area.
Texas and Australia are at opposite ends of the El Niño Southern Oscillation phenomenon. This means that it is highly likely that Texas and Australia have related responses to El Niño and La Niña. So we focused on them to shed more light on the relationship between the weather patterns of these two regions. La Nina pushes typical weather conditions to an intense extreme. For example, during the 2011 La Nina, Texas dealt with drought and wildfire conditions, while Australia saw high records of precipitation and flash flooding. So there's an inverse relationship. Looking into both these regions has helped us understand that floods and droughts are not mutually exclusive phenomena. We learned that both are dynamic events that occur in parallel and are affected by many of the same climate-driven factors. And ultimately, as you can see from the diagram, all of these climate disaster impacts are deeply interconnected, and our curiosity about the way that they interplay has led us to choose Texas and Australia as our two subjects for our research.
The MODIS sensor on Terra measures land surface temperature daily. Here, we have graphed this data for the past 22 years, along with the mean temperatures for each region. These GIFs give a more visual depiction of land surface temperature. This GIF includes 2011, an El Niño year. You can see that when Australia's land surface temperature is colder, or more purple, Texas becomes warmer, or redder. The phenomenon causes opposite extremes for each region.
We continued our investigation by looking at wildfires, which have reached record levels both in Texas and Australia. As of this summer, there are 12 active wildfires in Texas, and 99% of the state is experiencing some form of drought. In Australia, the bushfire season has grown by nearly a month in the last 4 decades, and fire events are only becoming more extreme. The GIFs on the screen represent burned area over time in both locations from 2000 to 2021. They show that West, North, and South Texas have experienced most of the state's extreme wildfire, and that in Australia, most fire events take place up north. One key thing to note here is that places that aren't experiencing as much wildfire tend to be more densely populated, so that would include East Texas and the lower half of Australia. Burned area has greatly increased in both locations, which was evident when we compared maps from 2000 with those from 2021 for Texas, and as you can see here for Australia. Next, we have a graph of total burned area over time, which allows us to see the burn data for specific years. One thing that was immediately apparent to us was that 2011 had an especially bad wildfire season in both locations, which was consistent with the record land surface temperatures that were recorded for that year. On that note, looking at the drought maps for 2010 and 2011, you can see the increase in drought levels that occurred in central Texas. And for Australia, drought extended much further east over the course of that year. Similarly, the burned area maps show a much greater burned area than those from adjacent years. Texas was hit hard from the beginning of the year, as shown by the volume of lighter points on the map, while Australia's wildfire season intensified in September, which is why there is a large number of orange and red pixels on the map. So, apart from observing overall changes in burned area for both locations, we also wanted to know which parts of Texas and Australia had been most affected by wildfire over the last 20 years. To figure that out, we split the territories into ecoregions and calculated the average number of square kilometers burned in each ecoregion between 2000 and 2021. In Texas, the areas with the highest average burned area were the Western Gulf Coastal Plain, which is down south, the southwestern tablelands up north, and the Edwards Plateau in central Texas. In Australia, which has nearly 40 ecoregions, the top 3 were the Kimberley Tropical Savanna, the Great Sandy Tanami Desert, and the Carpentaria Tropical Savanna, which are all in North Australia.
Next, let's talk about vegetation. Specifically, we can measure it with the Normalized Difference Vegetation Index, or NDVI for short. Essentially, it's a numerical representation of the vegetative health of a region, where higher values correlate with greener vegetation. It ranges from -1 to 1, and negative values show that the plants are dead or inanimate. We have low values for unhealthy plants and high values for optimally healthy plants. With this in mind, we can take a look to the right, where I created a graph that shows the relationship between Texan and Australian NDVI over the past 20 years. As we noted earlier, there's an inverse relationship between these climate disaster impacts. So whenever Texas NDVI is decreasing, Australian NDVI is increasing. That trend takes hold massively here, but it's important to note that it converges in 2001, 2011, and we can see it beginning to converge again as we approach the 2022 through 2023 La Nina phenomenon. So this shows that there's a trend of convergence in the La Nina years, and that's going to help us make predictions moving forward into this next season. And if you found that interesting, here's a GIF of the graph in the last slide where you can see the patterns play out visually over time.
Another important aspect of land to consider is surface soil moisture, which is also known as SSM. SSM is the total amount of water, including water vapor, in an unsaturated soil. I used the NASA USDA Enhanced SMAP Global Soil Moisture Dataset to generate soil moisture maps on Google Earth Engine, like this map of Texas. Soil moisture levels are important indicators of drought, as low levels are a sign of a risk for depleted soil moisture that may eventually lead to plants not maturing to their potential or permanently wilting and dying. Over the past few years, soil moisture levels have drastically decreased, as can be seen by these two visualizations. Through analyzing SMAP data, I discovered that as a result of the current La Niña pattern, in late 2021, soil moisture levels took a plunge and left Texas much drier than normal. Because of these soil moisture trends we visualized, we can predict that these levels will continue to decrease through the end of 2022, and that northern regions of Texas are more at risk for drought.
Humidity, the measure of moisture in the air, can also be used as an indicator for drought and fire risk. There are two ways that one can measure humidity: relative and specific humidity. Relative humidity is a percentage of water that air can hold at one particular moment at a specific temperature. Specific humidity is the ratio of water to surrounding air. While the relative humidity is most commonly used to observe weather, specific humidity can also be used for a similar purpose. This came in use during my research, as there was not always a reliable dataset that represented relative humidity for the areas I wanted to cover. By using relative max humidity data on Texas during El Niño and La Niña years, we can observe that Texas is more moist in the east during El Niño years, leading to more severe hurricanes. During La Niña years, like this year and last year, Texas appears drier, which explains why the majority of the state is currently experiencing a drought. For Australia, due to the lack of reliable relative humidity data, I used specific humidity to analyze how much humidity was present. In 2016 to 2017, El Niño years, Australia appears more brown and thereby more dry. In 2020 to 2021, La Niña years, Australia appears more white and thereby more moist. This displays the inverse relationship Australia holds with Texas and their humidity during El Niño and La Niña years.
Precipitation is an important indicator of global hurricane severity, giving us a measurement that we can use to analyze disasters like Hurricane Harvey in Texas, for example. Record high precipitation as part of tropical storms can cause flooding, while dry spells with low rainfall can cause drought. For our project, we looked at precipitation in Texas and Australia by using the Global Precipitation Measurement IMERG dataset, which dates back to 2000. We focused on precipitation measurements during hurricane and flooding seasons from 2017 to 2020, which happened to be a period of intense hurricane activity due to factors like the ongoing La Niña and global warming. As shown in these precipitation maps of Texas, precipitation was at record high levels in the Atlantic Gulf of Mexico region, correlating with high hurricane activity. We also mapped precipitation in Australia during the same period. Australia has various biomes, and as shown, its northern forest biome receives more average rainfall, while its southern desert biome is dry and more prone to drought. Here we see that in the north, the northern Australia is more prone to flooding and those sorts of impacts, while the south is more prone to drought-related issues like wildfires. In 2019 to 2020 in particular, there was a sudden drop in precipitation in the southern region, which led to intense wildfire activity. We also mapped precipitation in both Texas and Australia, as shown in this line chart, and this was in the year of 2017. We also mapped precipitation in 5 La Niña and heavy rainfall years between 2005 and 2021. Over time, we saw that precipitation in Texas has been increasing during hurricane season, which tends to be from around June to September. Meanwhile, precipitation has been at record lows during Australia's dry season from May to October. Using our analysis and current observations from the current 2022 La Niña, we can predict that these precipitation trends will continue, leading to increased flooding risk in eastern Texas and drought risk throughout parts of Australia.
Flooding connects to humidity, soil moisture, and precipitation. Severe flooding is caused by atmospheric conditions that lead to heavy rain or the rapid melting of snow and ice. Geography can also make an area more likely to flood. For example, areas near rivers and cities are often at risk for flash floods. Different situations that can cause floods include heavy rain, as mentioned by Shrima, storm surges, melting snow or ice, and dams or levees breaking. Using the Global Flood Database, which dates from 2000 to 2018, I mapped the flooded areas of Texas in the year of 2016. Although precipitation was at high levels due to severe hurricane activity in the 2017 La Nina, I found the global flood database to be an incomplete dataset, which could possibly be because of the cloud coverings during the extreme storm events. The brown color on the map represents the study area, and the red colors on the map represent the maximum extent of flood water during the event, which is the 2016 Atlantic hurricane season in this case. The heavy flooded areas on the East Coast and northeastern Texas correlate with the heavy rains of the period and with the high soil moisture and precipitation towards eastern Texas. In the same way, the global flood database was used to find heavy affected areas in Australia. This time, a 1-month period of March 2017 was examined due to its severe tropical storm period and high impact with the number of people displaced and the number of casualties. The coast of eastern Australia has a great flood extent as shown by the red coloring on the map. This also correlates with the high humidity on the eastern coast of Australia as shown by Shruti in the previous slides. High surface soil moisture levels increase the risk of flooding, especially in regions that experience more rain. On the left is a visualization of average surface soil moisture in Australia in 2020, and the black outlines highlight different ecoregions, which are areas where ecosystems are generally similar. On the right is a time series Anita generated using Matplot, which displays surface soil moisture levels from 2015 to 2022.
This is a time lapse of the average soil moisture levels every month in Australia from 2018 to 2021. Through this visualization, I concluded that flooding season in the northern areas of Australia tend to be during the beginning months of the year, especially February and March, whereas southern regions of Australia experience increased flooding in the later months of the year, July and August. Through this time lapse, I also discovered that over the past 6 years, flooding may have worsened as soil moisture levels have increased. And because of those higher soil moisture levels in recent years, I was curious to check out the surface soil moisture anomalies, or SSMA for short. Darker regions on these time lapses show that moisture levels are further from the mean soil moisture at that date. And as you can see, the number of drastic anomalies in soil moisture has significantly increased since 2018.
After calculating the ecoregions with the greatest burned area and evaluating relevant climate conditions, we came to the conclusion that these particular areas featured on the map are at risk for long-term wildfire exposure. If Texas or Australia were to allocate resources for wildfire prevention, we believe it would be highly beneficial for them to focus on these locations.
We also wanted to create a tool that individuals and communities could use to assess flood risk in their own communities. Here, you can see flood risk maps that we created based on 2 significant parameters contributing to flood severity, including soil moisture and precipitation. These maps also feature areas that have been flooded in the past, giving users an idea of historical flooding and how those areas could be affected in the near future. As for next steps, we hope to analyze other factors that could affect the extent of flood damage on communities, such as population density and impervious surface cover. Looking into these data sets will allow us to create tools that individuals and scientists can use to plan ahead for natural disasters, preventing and reducing harmful impacts.
After generating our final risk maps, I developed a web app using HTML and CSS to highlight our most important findings in a simpler and easier to understand manner for the greater public. We included all the important maps and time series we visualized during the internship, and we included essential background info for our research. And you can check it out by scanning this QR code.
Our primary challenge was having to bond as a group in such short notice. Coming from different states around the country, we had to quickly learn how to collaborate in order to learn new skills, work through problems, and develop meaningful research as a team. For our project, there was a steep learning curve to understand code for accessing and mapping data using Google Earth Engine. Together, we had to work hard as a team to understand documentation written in JavaScript and translate it into Python for use in Google Colab. This made it hard to troubleshoot certain issues we had, since most solutions were JavaScript exclusive. However, this experience of working on a challenging topic in a team environment was valuable experience that we can take into the future.
Overall, the SEAS internship program is an incredible opportunity for students like us to get hands-on experience in the field of earth science, apply skills we've learned in high school, and gain valuable insight and connections with professionals in the field. The program has had a significant impact on each and every one of us. The life skills and hands-on experience we take away from this program will serve us through college and beyond. We would like to extend a thank you to NASA and the Texas Space Grant Consortium for hosting the SEAS program, the Center for Space Research for providing their facility, our amazing mentor Teresa Howard for her guidance and expertise throughout the internship, and you, the audience, for attending our presentation. Thank you so much.
Great information. We would invite your team to please turn on their cameras and unmute their mics. We have several questions for your team. First of all, the first question is, what was your favorite part of this project?
I can start for this one. Apart from working with such an incredible team, my favorite part was calculating total burned area for specific ecoregions, because I got to work with pandas and CSV files for the first time, and it was really rewarding to visualize the results in a risk map.
And what was the biggest challenge mapping with Google Earth Engine?
I can take this one.
Okay, go ahead, Ethan.
Okay, the biggest challenge for Google Earth Engine was producing the layered risk maps. So those are made difficult not only because we were combining multiple factors to assess risk of certain climate disasters in different areas, but also we were limited in computing power from Google Earth Engine. So that made it difficult to produce the maps in a timely manner. So sometimes it took a while, and it just took a long time for maps to display so we could see if they had worked or not. And then also we were limited in the amount of data that we could process for the GIFs. And so that means we had to limit our time range a little bit for some of them to not display as much data.
And how do you think El Nino and La Nina patterns will be affected by global warming?
I can take this question. We did some reading and we found that because of global warming, El Nino and La Nina events will likely occur at a higher frequency and for longer amounts of time, which will cause more damage to the areas that they affect. For example, during La Nina events, the tropical areas of the Pacific Ocean will be warmer, which will basically increase global temperatures because more of the water will evaporate and therefore increase atmospheric temperature. And then during La Nina seasons, the opposite will occur, which will decrease global temperatures. And basically, to wrap up what I was saying, because of global warming, the effects of La Nina and El Nino will be more drastic than they already are, which is not a good thing.
And how did you create your data visualizations, your graphs, maps, animations?
I can take this one. If that's all right. So in order to create the data visualizations, it depends on exactly how we're trying to visualize it. For the graphs and the maps, we used specifically for the charts, we call them time series charts. We use Matplotlib. So we were able to create the bar graphs and the line graphs of the data over time. And then for the maps and animations, we use Gmap, which is a module that we installed, which helps connect Python and Google Earth Engine. And the animations were used with a function called timelapse to create the GIFs over time. And then the maps had a built-in function in Gmap so that we could map the data that we were trying to express from the data set.
Great. And how did you choose the data sets that you plan to work with?
I can take this one. So the main environmental concerns we decided to focus on were heat data and water data. So for water data, we use data sets such as soil moisture, flooding, and precipitation to find out which areas were at most risk for floods. And then for heat data, we chose data sets that would reflect areas that would be at more risk for wildfires, such as a wildfire map, NDVI, and also soil moisture.
And how would the flood risk maps be useful and applied in the future?
Yeah, I can take this question. So what we did to create those maps was basically masking certain pixels in images of precipitation and soil moisture data sets but we also included past flooding areas on those maps. So essentially these maps give our viewers an idea of historical disaster impacts, but also tells them how those same areas could be affected in the future. So we believe that policymakers in particular can use our maps to concentrate green infrastructure development in high flood risk areas. And also it's very important for scientists to be able to communicate information about floods to citizens more effectively. And I will pass it on to Helen to elaborate a bit more on that.
Yeah, so in addition, the maps could also be used as tools that would be especially useful for at-risk communities and helping them prevent harmful consequences by recognizing flood dangers earlier on. And so the additions that we talked about of factors like population density and or like impervious surface covers would also help in this process.
Well, you did a wonderful job on your research, and thank you for sharing your research with us today. So we invite all of our viewers to watch the highlights from the James Webb Telescope first images, followed by NASA Sea's alumni videos highlighting their accomplishments and the value of the internship during this 20-minute intermission. We will continue with student presentations at 2:30.
Every image is a new discovery, and each will give humanity a view of the universe that we've never seen before.
This image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And, you know, it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before.
These images are going to remind the world that America can do big things. And they remind the American people, especially our children, that there's nothing beyond our capacity, nothing beyond our capacity.
Today represents an exciting new chapter in the exploration of our universe. This telescope is one of humanity's great engineering achievements.
This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. First of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars.
See lots of individual stars in there actually resolved as point sources, which is remarkable. And then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust, which is being heated up in the collision between those galaxies.
What you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres. There's evidence of clouds and hazes because the water features are not quite as large as we predicted.
Eye-opening. Emboldening. Unbelievable.
Transformational.
fun.
Fantastic.
Enlightening.
Inspiring.
Inspiring. Inspiring. I am inspired by the competence of the students, by the growth during the time that they're here, and by their enthusiasm for the program.
The STEM Enhancement in Earth Science program that NASA, the University of Texas, and the Texas Space Grant Consortium is offering really does provide students that spark and the excitement about pursuing STEM degrees in college.
SEAS really opened my eyes to sort of aerospace engineering and planetary science, which is something that I really just hadn't had exposure to.
The work that we did on our internships is related to the work that I'd like to be doing the rest of my life, and it really solidified my confidence in the fact that this is what I want to do when I grow up.
Made space science seem a lot more practical and tangible than it would have if I had just read about it in a textbook.
They are actually helping the scientists analyze Earth-observing satellite data that science mission experts are providing.
There are very few chances for students of my age to work on real and highly relevant projects, and every project within the SEAS program grants this rare opportunity.
It's one thing to have a question and Google it, but it's another thing to have a question about Mars and have someone who actually studies Mars for a living answer.
But it's really, really hands-on. You get to work on real science, on real NASA projects with real NASA scientists. Just a really incredible experience that you're not going to find anywhere else, and that's a very rare opportunity for high schoolers.
And I will never be able to thank everyone who made this possible with words, because from this moment on, my future has been rewritten, and I'm just very thankful.
Hi, my name is Saneri Patel.
My name is Aiden McLaughlin.
My name is Anavi Opal.
I'm Keegan Fong. I'm from Memphis, Tennessee.
From San Jose, California.
I'm from Palmer, Alaska.
And I'm from Seattle, Washington.
From Montclair, New Jersey. And this summer I became a NASA scientist.
And this summer I became a NASA aerospace engineer.
I became a NASA researcher.
I became a NASA astronomer.
My name is Nikki from Columbia, South Carolina. This summer I became a NASA researcher.
I decided to apply because I've never had the opportunity to learn about space exploration or astronomy other than from a book or from a classroom setting, but I thought that this internship would give me the opportunity to have a more hands-on experience.
My school didn't offer a lot of opportunities to learn about aerospace or astronomy, so I thought that this internship was a good way to learn more about the subject area that I wanted to pursue later in life.
And I decided to apply because the level and the depth of the research being done in SEAS was unparalleled by any other program.
To actually have the opportunity to work with NASA scientists and professionals in the STEM industry, it seemed way too good to be true.
After working alongside scientists and engineers at the Center for Space Research and listening to dozens of professionals share about their jobs, I now have a better understanding of what my career might look like someday and of the steps I need to take to get there.
The internship helped me prepare for my future career by allowing us to work together in a team to complete a project with both time and resource constraints. We engaged in serious debugging efforts involved with real-world programming, cultivating patience and attention to detail.
It was unlike any other team project I had ever been a part of, because every one of us was so passionate and excited about what we were working on.
I'm really glad that I was able to have this experience before my senior year, because I don't know what position I would be in if it weren't for this internship.
And I feel that I have all the tools that are necessary now for
pursuing a job at NASA in the future.
So going into this program, I honestly wasn't entirely sure what I wanted to do. Definitely coming out of this program, I know that I want to be an aerospace engineer. I want to work in the aerospace industry. I want to be a part of what I was able to experience with the program. And so that guidance specifically is something that I have to thank the internship for, because without the program, I would still probably be lost trying to figure out what I want to do as a career and major in college.
But it has also made me consider other careers relating to space, such as engineering and planetary science. I most likely wouldn't have considered these other options if it hadn't been for the experiences that I had at SEAS.
This internship has really reinforced how I see my future career, in that it has provided me the confidence to continue with computer science.
SEAS has reinforced the idea that I want to work with NASA, and it also told me that it's possible. Before SEAS, I thought I was overreaching by thinking I'd be able to work with the great minds at NASA, but after SEAS, I know that I can do it because I have done it and it was amazing and I'd love to do it again.
The SEAS internship led me to realize that my dreams of someday working for NASA are much more within reach than I had once thought. I don't have to be a genius to work for NASA. I just have to be dedicated and willing to work hard.
They showed me how doing what you love can change the world.
NASA SEAS helped me become a software engineer.
They really helped me gain my confidence in the STEM field and made me realize that I could translate my passion for science into a successful career.
The STEM Enhancement in Earth and Space Science Internship is an intensive, nationally competitive program for 10th and 11th grade students. SEAS, a partnership between the University of Texas at Austin, Texas Space Grant, and NASA, provides students the opportunity to conduct authentic research while being mentored by NASA's subject matter experts.
SEAS helped me solidify my desire to work in the space industry.
It was so surreal to have the opportunity to meet NASA scientists and engineers, as well as meet other students as passionate about STEM as I was.
SEAS helped me improve my teamwork and collaboration skills by placing me in a professional environment early in my career.
90% of SEAS alumni have gone on to major in STEM in college, preparing them for careers in science, technology, engineering, and math.
SEAS gave me the confidence to pursue further research opportunities in science and technology.
The SEAS program has helped me become a better researcher and scientist. I use the skills that I learned within the SEAS program that summer every day in my current field of biomedical sciences.
Former SEAS interns have gone on to become Back to Space student ambassadors, presented at professional conferences, won national competitions, attended Ivy League schools, received scholarships, and interned with companies such as Google and NASA.
SEAS has helped me get into college and land internships.
I first heard of NASA's Pathways co-op program on the SEAS tour, and I'm happy to say that I started my first term as a NASA co-op this spring.
The SEAS program in 2016 was my first experience with programming or any sort of computer science, and now I am studying computer science as a junior at Vanderbilt.
I helped start an astronomy club at my school after SEAS. SEAS helped me become more ambitious and believe in myself more, which I'm always thankful for.
These amazing students attribute their experience and their growth to participating in the SEAS program. Here's an example of how students have been affected by this nationally recognized internship.
I always cite SEAS as the program that put me on the path that I'm on now.
And I think it was an experience that I would never forget.
But best of all, SEAS reminded me that there's so much more for me to learn. And I was left feeling excited for what discoveries the future will hold.
Overall, the Texas Space Grant Consortium through NASA and the SEAS program has helped me become a more confident and better student. And through the amazing network that SEAS helped me develop, that has translated into me becoming a better person and contributor to the world of STEM.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
Welcome back to the SEAS 2022 Science Symposium. Our next project is the Moon Exploration and Habitation Group. The interns worked as a team to investigate and design Lunar Operations Station. Their success in this endeavor required many areas of expertise, and each intern will look on a variety of engineering or science roles that will make up one cohesive design team. Through gaining knowledge of the most pressing and current scientific questions about the moon, the team chose the most appropriate landing site that will not only provide the best opportunity to conduct science, but also one that will provide the valuable in situ resources that will be needed to sustain human habitation on the lunar surface. A special thanks to Dr. Ernest Lewis of the Astromaterials team at NASA Johnson Space Center for his commitment and dedication to this project. Please welcome the Development of Exploration of a Lunar Operations Stations team.
Good afternoon and welcome to everyone here in our audience today. We are the NASA SEAS 2022 Moon Exploration and Habitation team, and we are proud to present to you Delos, our design for a manned lunar base dedicated to scientific research and exploration.
Hi, my name is Blake Brown, and I'm a rising junior from Fort Worth, Texas.
Hi, my name is Eric Fabian Cardenas, and I'm from Ronda, Texas.
Hi, I'm Taylor Gomez. I'm from Spindora, Texas, and I will be a senior.
Hello, my name is Zyra Zaka, and I'm a rising senior from Medford, Oregon.
Oh, I'm Kylan Williams, and I'm a rising senior from Luz, Florida.
The name Delos is derived from ancient Greek mythology. The word itself means something that can be seen, and it is the name of the wandering island that was the birthplace of immortal twins Apollo and Artemis. In our mission, Delos is an acronym for the development and exploration of a lunar operations system. Decades of scientific research done by Apollo and the upcoming Artemis missions have trailblazed a path to support Delos. Without the innovative work done by the people behind these missions, Delos and future missions beyond the moon would not be possible.
The objectives of the Delos lunar base will be broken into several parts. The first step will be landing the prerequisite modules on the moon. Secondly, the first astronauts will move and connect the portable base structures into the lunar base. After constructing the base, the primary mission will be prepping the laboratory for sustainable human presence and preparing the life support systems. After this, the main objective of the base will be to conduct vital research and explore the surface of the moon. Finally, the work done on the lunar surface will help prepare and propel humanity to prepare for a manned mission to Mars.
Mission sits on the foundation that the Artemis mission and all of its components such as the SLS rocket, Orion capsule, and space funding are established. This mission will be conducted in 3-month-long periods in a base with a volume size of 628 cubic meters with a required power supply of at least 20 kilowatts per day. So why humans? Robots are more resilient, more powerful, and easier to control than humans. However, humans are adaptable and have a consciousness that AI cannot replicate. It is imperative that humans do what they have been doing since the beginning of time, learning and exploring, whether it be the Earth, Moon, or Mars.
Our research approach was really collaborative. First, we identified different problems we face on the lunar surface, and then we worked towards brainstorming ideas, researching the feasibility of those ideas, hitting to a final design, and then backtracking to overcome and improve.
This is the Gantt chart illustrating our team's progress, as well as pictures of us and Dr. Lewis seeing actual Mars meteorites that illustrate some of the research behind our project.
The quad chart gives a simplified overview of our project. To start with, our objective is to develop a sustainable scientific laboratory that can support a long-term human presence on the lunar surface. Having manned workspaces in close proximity to target samples will not only increase the quality of samples, but also the extent of potential lunar surface data that can be collected for future ISR use. In the top right-hand corner, we have a list from one of our brainstorming meetings and a top view render of our finalized lunar base. The entire mission largely depends on the success of the Artemis mission, and after Delos is established, we will also include a Mars Forward test facility that can be used to test technology for future Mars missions and beyond. Within this facility, we can test spacesuits designed for pressure in a Martian environment, among many other future technology that would be necessary to expand human space exploration.
This is a site that we have chosen. This site was based off several parameters, including mean elevation and topography, illuminance, direct communication with Earth, conformation of water ice, and close proximity to permanently shadowed regions, which will be invaluable for geologic studies and purposes. This site chosen is a wide, flat space and is located 6.1 kilometers south of the Ibn Baj crater and 106.7 kilometers west of the rim of Shackleton crater and the geographic south pole of the Moon. Some of the upcoming science objectives for the Delos lunar base include geology, such as sample collection of volatiles and minerals from permanently shadowed regions, and lunar materials, such as investigating the extraction and processing of raw lunar materials, as well as ISRU, such as utilizing the resources on the Moon and forming usable products. Human research, exploring the human effects of partial gravity and extraterrestrial habitation, as well as radiation. Biology, further research and study into biological processes to sustain a human presence on the Moon. And lastly, novel technology and architecture that will pioneer new and novel technologies to explore and thrive on the Moon.
This is a model of our base that I designed in the 3D modeling software Blender. You can see the two solid spherical modules, the Central Operations and Resource Environment, or CORE module, and the Excursion modules, and then the two inflatable modules, which are the Geology Lab and the Life Sciences Lab. Each is connected by accordion-like tubes so that the base is modular and connecting the inflatable tubes is simple and straightforward.
The material chosen for the whole of the solid pressurized modules is 2219 aluminum alloy, chose for its tensile strength, thermal stability, and it being well tested on previous space missions. The outer layer of the base will be covered with a thermal blanket to reflect solar radiation, followed by a layer of Kevlar to protect the base from ejected lunar dust and micrometeorites. After this will be the layers of aluminum and polyethylene, which will give structure to the base and provide some radiation shielding, due to polyethylene's high hydrogen content. Finally, several redundant layers will help prevent pressure loss and leaks. These modules will be filled with a mixture of gases specifically tailored to meet the astronauts' needs. Maintaining the exact pressure and composition of these gases will be critical to the astronauts' mission and survival, and so protecting the interior space of the habitat from the outside will be of utmost importance. To support the astronauts via life support systems, we will be using technology and systems that have been well developed and tested in heritage space missions. Oxygen will be generated via electrolysis of water, which can be used to separate hydrogen for rocket fuel and oxygen for breathing. In addition, carbon dioxide scrubbers will prevent the continuous buildup of CO2 using regenerative absorbent beds. Finally, the base will need a trace contaminant control systems to monitor the buildup of over 200 trace gases, including methane, ammonia, and formaldehyde.
One of the most crucial elements on board the base will be the water reclamation system. Water, being both an incredibly heavy and vital resource, will be recycled and recondensed whenever possible. In addition, small amounts of water will need to be continually replenished on board the base from Earth or extracted from lunar ice.
During our research, we found it imperative to address radiation and micrometeorites because they are some of the biggest hazards that the crew will be facing on the lunar surface. Radiation can lead to degenerative diseases and mental health issues because the charged particles going through your brainwaves can lead to extreme bouts of anxiety and depression, which would be very detrimental for a crew in an isolated environment. Even further, micrometeorites can lead to damage to the base. To combat this, we would ideally have a approximately 22 centimeter thick layer of polyethylene to combat the radiation. Although this wouldn't be feasible right off the bat, it is something to work towards to protect the crew. An additional protective layer of lunar regolith would be used as another portion of radiation shielding with its components of aluminum, while also being a protective shell against micrometeorite impacts and protect the base rather than leaving it vulnerable. We'll also have additional sensors that will be tracking the radiation exposure of the crew, while also having other sensors to look at trajectories and see where micrometeorites might impact and harm the base.
Here are the 5 main modules we'll be discussing in our base. The Central Operations and Resource Environment, or CORE, module, the Excursion module, the Geology Lab, the Bio Bay, and support systems.
Many of the essential support systems, such as oxygen generation, power, food storage, thermal controls, waste management, and other important systems vital to the crew's survival. The module will house the compressed oxygen and nitrogen canisters, as well as the crew's sleeping quarters and exercise area.
The excursion module is the secondary, smaller, polyethylene dome that will act as the workshop area of the base, where the suit ports, human-robot interface, tool shop, and access to the MMSEV will be housed.
The geology lab will be inflatable. As we mentioned before, the Delos lunar base has 2 laboratories. This one is for geology, and there's another for life sciences. While it would be best to analyze all lunar regolith in Earth labs, only a small percentage of collected samples will be conveyable back to Earth via the human launch system. Because of this, much analysis on lunar regolith will need to be done on board the base. To do this, the base's geology laboratory is equipped with a surface samples glove box, a gaseous nitrogen connection, a sample preparation kit, a polarizing microscope, a scanning electron microscope, dual-use spectrometers and meters, and other various geological analysis tools.
The biology lab will be inflatable. Our design builds on the design of Robert L. Howard Jr. and biology science on the ISS. Both laboratories will consist of a modular payload drawers where scientists can send self-contained experiments. The astronauts on base will simply set them up in the racks and monitor them as they run. The experiments will be delivered on resupply missions. The Life Sciences Laboratory module of Delos Base will include 1 human research payload rack and 1 non-human biological research payload rack. The research module will be for determining how human bodies adapt and change in harsh extraterrestrial environments. There are 5 main problems with the module we will be monitoring: radiation, isolation and confinement, distance from Earth, gravity, and hostile and enclosed environments. It will also include a cell culture, animal studies module, fruit fly study containers, a cryogenic drawer locker incubator, and a general workspace for general biology research.
When in isolation, it is very plausible that astronauts will fall to bouts of anxiety, claustrophobia, and even depression. To combat this, we wanted our base to have a center around mental health and ensuring that our astronauts are taken care of. So we would like to suggest psychological evaluations along with appropriate medication, since this is going to be a longer trip and we need to prepare for these different instances. Even further, part of those medications would include sedatives, and we also want to ensure that the communication system is able to support communications with an astronaut's family.
The moon has 1/6 of the gravitational force compared to the Earth, and because of this, it has a major effect on the astronauts. The astronauts will lose approximately 1.5% of their bone mass per day, and to address this, similar to the ISS, the astronauts will need to work out immensely. A total of about 2.3 hours of exercise a day is needed to help keep their bones strong. Additionally, their diets also contribute greatly. Lots of calcium and vitamin D are needed to help keep their bones strong, commonly found in fish and mushrooms.
A lack of sleep significantly and negatively impacts cognitive abilities, neurobehavioral function, and overall health. It also increases risks of accidents and incidents happening that could endanger the astronauts. Irregular workload demands and the loss of the 24-hour daylight cycle are 2 factors that could disrupt the circadian rhythm. Some additional elements that impact the quality of sleep astronauts may receive include microgravity and space motion sickness. In order to combat this lack of sleep, lighting within the core module will be used to mimic the 24-hour daylight cycle.
To power our base, we will use both kilopower reactors and solar power. The PILE system by NASA is a more efficient answer to solar cells on a lunar surface. However, the sun will not always be facing our base, and so a secondary form of power is necessary. The kilopower reactor using Starling technology, CRUSTY system, creates energy by the process of nuclear fission. Using a uranium-235 core and a boron-carbon control rod, when the 2 elements interact, they cause a nuclear reaction generating electricity. The power system can create up to 10 kilowatts per day, and a couple of them have the potential to power the entire base and our rovers.
Moon dust will likely be one of the greatest challenges for our aspiring astronauts and scientists that they will face on the moon. As became evident even during the short Apollo missions, the microscopic lunar dust fragments have the potential to quickly clog seals, zippers, and movable parts. The complex nature of this lunar base, as well as extended extravehicular activities and robotic missions, will make prime targets for lunar dust damage. Additionally, while there is little data on the toxicological effects of moon dust, the microscopic particles can easily pose a respiratory hazard to the astronauts. Some of the potential solutions include basic tools such as vacuum cleaners and brushes, as well as suits that never fully enter the habitat. However, the human researchers on the moon will have the opportunity to study and test novel technologies such as electrostatic propulsion systems to repel the charged dust directly woven into the spacesuits and fabric of the lunar base.
The Lunar Reconnaissance Orbiter has been orbiting the moon since 2009 and has been a very valuable resource for data about lunar terrain and temperatures. Because of LRO, we know that the moon can reach temperatures of up to 120 degrees Celsius and as low as negative 130 degrees Celsius. The active thermal control system will be used to control interior temperature by controlling the location and intensity of heat, by pumping liquid ammonia through a system of plumbing throughout the base.
Most geological analyses will need to be done on the base as opposed to on Earth. Here the astronauts will be looking for volatiles and water on the surface. To do it, the base will be equipped with a few main tools: a polarizing microscope for molecular analyses of samples, spectrometers to determine what a sample is via its light spectra, and a laser-induced breakdown spectroscopy tool.
As part of the research investigations on the moon, humans will not only study biological processes in a unique environment, but will also pioneer new technology to be used on future missions to Mars. The researchers will use state-of-the-art biological instruments and advanced techniques such as genetic engineering and aeroponics to innovate and discover new solutions to sustaining life and growing food on other planets or celestial bodies. The study on the moon is processing lunar dust and other raw materials into usable forms. Electric or solar furnaces can heat the lunar dust to form glass or ceramics. Furthermore, the metal oxides comprising the majority of lunar dust can be converted directly into solid metal with oxygen as a byproduct, such as calcium, magnesium, aluminum, or titanium. Additionally, the moon may contain trace amounts of rare earth metals which could be harvested and shipped back to Earth.
In situ resource utilization are rovers and satellites that harness resources from the moon to use on the moon. The Viper, a volatile investigating polar exploration rover, is designed to discover frozen water deep in the moon's PSRs. It uses four main tools: a neutron spectrometer system to use to detect water, Trident, a drill designed to go through regolith and potential ice, and two spectrometer devices used to analyze collect samples.
When on the moon, there is also a necessity for transportation. We decided to use the Lunar Terrain Vehicle, particularly because of its autonomous driving, as well as its ability to have scientific payloads. We also want to use the SEV because it is designed to explore with minimal time needed outside of the rover, and it also has a robotic arm. We also wanted to use the Athlete because it can support loading and lifting heavy vehicles. It can split into two parts. This is a segue into the triathlete, and each wheel doubles as a limb for tools, which can be really useful, and the versatility for everything that an astronaut needs.
The new age of spaceflight is among us, and frankly, it's overdue. The moon and eventually Mars will be explored and researched by humans. It's only a matter of time. Artemis is a slight sparkle of hope into the vast future of space travel, and our base acts as a stepping stone into that future.
Thank you to our project mentor, Dr. Ernest Lewis, for all of his help and support with designing our lunar base. We would also like to thank all those who gave their advice and especially like to thank Miss Selena Miller and Miss Margaret Baggio for all of the work that they do for the SEAS program, as well as NASA, everyone who helped out with the SEAS program, the Texas Space Grant Consortium, and the Center for Space Research. Now, we want to tell you a little bit about what the SEAS program meant for us.
The SEAS internship was incredibly enriching. I most of all enjoyed the awesome team members and friends I met here. It was great.
The SEAS program was truly an invaluable experience. It was amazing to meet like-minded individuals who are all passionate about STEM and excited to learn more. Throughout this program, I became more confident in my own abilities as well as the career that I want to continue to pursue.
For me, SEAS was an incredible and eye-opening opportunity that gave me the chance to truly learn more about STEM.
This SEAS experience has been astonishing. Over the past 2 weeks, I feel like I have learned so much, and the resources and connections that I've made will last me a lifetime. Special thanks to everybody that has helped me along the way.
I really liked the SEAS internship because it gave me the opportunity to work with people from across the nation that were passionate about STEM. I also enjoyed listening to the speakers and hearing about their experiences in their different fields. One of the challenges I faced was meeting a group of people I did not know on that first day and being expected to go straight to work. But this experience was very valuable because it taught me about communication, team building, and especially just working hard to break the ice with people you don't know.
Thank you for the Moon Exploration Team.
Thank you all for your presentation. I want to invite all team members to turn on their cameras and also to unmute your mics. We have several questions for you. So the first question is, what is the significance of the Mars Forward Test Facility?
I think I can answer that question. Our base acts not only as a laboratory for biological and geological studies, but also as a theoretical stepping stone and practice run for future Mars exploration.
And how do the effects of partial gravity have on astronauts' sleep differ from the effects of microgravity?
I can take this one. So there is a slight difference in that there is some gravity on the moon. So unlike the ISS, astronauts will not be floating in kind of the sleeping bags that they had there that were strapped to the wall. They will have something closer to the hammocks that the Apollo missions had and actual beds. And they won't experience the space motion sickness and microgravity. Those factors won't be as significant. And the greatest impactor will be the light cycle. So that is something that we will focus. And then the actual effects of sleep and partial gravity have not been researched very much. And so that will be something that we will heavily focus on in our human research lab.
What are the biggest differences between the lunar and Martian environments that you need to test?
I believe I can answer this one. So one of the biggest differences between the lunar environment and Mars is the chemical composition of the lunar soil, as well as the much lower gravity. I believe the moon's gravity is about 1/2 of that of Mars. And it'll be much easier to travel to the moon. So it will serve as a good stepping stone to test systems that will later be used in the Martian environment.
So why is it important to have humans on site to test experiments with lunar samples as opposed to sending robots for a sample return mission? Anybody want to answer that one?
I believe Kylan's mic is having some problems.
So let's go to the next question and we see if Kylan can get his mic to work. Why do you think that there is a greater emphasis on mental health on this mission than in past missions like long stays on the International Space Station?
I can take this one. So it is really important to address the mental health of astronauts, particularly because it is more distant from Earth and it's more isolated. So any bouts of mental health issues such as anxiety and depression need to be handled on site, and there's no option to just schedule a mission and give them supplies or bring the astronaut back. It has to be carefully timed and meticulously addressed in order for it to be successfully overcome.
Great. Kylan, we'll see if your microphone is working now. What are some of the next steps for lunar habitation? It looks like he's still frozen. So does someone else want to answer that one?
I can expand on that a little bit. So after Artemis and this base is established, we will have more opportunity to test some of the Mars Forward technology, and this will help significantly with expanding human exploration to Mars and beyond. And so that is one of the greatest contributors that this base can provide, is the ability for humans to expand their presence in space.
Great. Well, I appreciate your research. I enjoyed your presentation, and it was nice to hear from all of you. So the next team is the Mars Rover Utilization team. They designed a mission to explore in situ resource utilization on Mars. Key goals included studying Mars habitability, seeking signs of past microbial life, collecting and caching samples, and preparing for future human missions. Interns will select a landing site for a hypothetical rover mission, decide on the instrument payload, determine regions of interest, and plot a traverse for their rover using remote sensing data of their chosen landing site. Our thanks to S.J. Ralston with Jacobs Technology at NASA Johnson Space Center for guidance and leadership for the Mars utilization team. So please join me in welcoming the Mars rover utilization team and their project investigating the applications of in situ resource utilization for future crewed Mars missions.
Exploration has driven society since the beginning of time. Our thirst for discovery and exploring the unknown makes us human. Now that the world is embarking on its new odyssey to Mars, we must take the proper measures to promote safety and sustainability for generations to come. That is why the Mars Rover Research Utilization Team has been exploring the feasibility of research utilization on Mars. And today, we are going to be giving a brief overview about what we've been doing these past few weeks.
Today, we will be going over the purpose of ISRU, its applications to a future crewed mission to Mars and beyond, and how this all ties into a joint rover and helicopter mission.
This is our team. Hi, I'm Andre Nunes, and I'm from Silver Spring, Maryland.
Hi, my name is Giselle Ransom. I'm a rising junior, and I live in Hurst, Texas.
Hello, my name is Haley Peterson, and I'm a rising junior from Waters Meet, Michigan.
Hi, my name is Lily Segna, and I'm a rising senior from Portland, Oregon.
I'm Matthew Martinez, and I'm from Las Piedras, Puerto Rico.
Hi, my name is Zara Renisi, and I'm a rising junior from Miami, Florida.
And here's our background on Mars, minerals, and ISRU, and I'll hand it off to Matthew.
You're probably wondering, why should we care about this? Well, this mission will expand our knowledge as a collective whole and revolutionize the way we study and think about celestial objects. With this, we will test how good we are breaking barriers.
These are the rovers that inspired our rover design and what a rover should be looking for, such as various useful minerals and radiation levels.
Now moving on to Mars history of the environment. Now, we want to consider many conditions and factors in Mars' environment, including atmosphere, terrain, temperatures, water, weather, gravity, physical features, radiation, and living organisms. Now, the atmosphere in Mars is very thin, temperatures are very cold, terrain's very tough, water is very sparse, and everything about that makes missions very hard. So we have to work around all these factors.
Due to Mars' extremely thin atmosphere, it is under constant exposure from different types of radiations from space. This can lead to increased threat levels from events such as solar flares, which accelerate all energetic particles within its vicinity. This also means that it has no protection from the UV radiations that are coming from the sun. Additionally, the effect that space travel has on our cardiovascular system can be devastating. While we're in space, we experience a free fall sensation, which disables our blood vessels' ability to properly retract and open, causing them to stay small and tight while we're in space. This will prevent proper blood flow from reaching all parts of our body. Also, the distance between Earth and Mars and the time it takes to travel between the two planets means that if something goes wrong, we most likely won't be able to provide support in time.
ISRU is the process of collecting, processing, and the use of materials, such as what MOXIE does. MOXIE stands for Mars Oxygen In Situ Resource Utilization Experiment, which converts carbon dioxide into oxygen and is the first ISRU technology demonstration on Mars.
During our research, we found several useful minerals on the Martian surface. These are olivine, iron oxides, sulfates, carbonates, ice, and phyllosilicates. These can be used for a variety of reasons, like construction, iron, oxygen, water resources, tools and parts manufacturing, cement, and most importantly, propellant, which can help us getting in and out of the Martian surface.
With all that in mind, let's talk about our primary mission objectives. Since our project is centered around space exploration, it is prudent to align our goals with those of NASA and the Human Exploration and Operation Program, investigating and developing technology to sustain human presence beyond the current limits of humankind. But what sets our project apart from previous Mars missions? Rovers like Perseverance and Curiosity have focused on answering questions about the environment on Mars, both past and present. Instead, our mission turns towards the future. How can we sustain a crewed mission on Mars? However, it takes far more than just a goal to create an entire Mars mission. Let's talk about our rover itself. We started with a mission patch. Drawn in the center is our rover, Valor, and off to the side is our Martian helicopter, Venture. We picked the name Valor to encompass NASA's nomenclature for Mars rovers, exemplifying a trait crucial to exploration.
Other than its main body, which hosts the brain and ChemCam, Valor's design features a mast and robotic arm to aid a few instruments in gathering data. This blueprint was made using a CAD-like software and gives a rough image of what the rover should look like.
Now we will introduce the instrument payload, which will be used by the Valor and Venture spacecraft. We will be talking about Adron. Adron was used on the ExoMars rover, and it will now be used by the Valor rover. It identifies and analyzes subsurface water and hydrated mineral abundance for extraction. The purpose of this instrument is to analyze subsurface water and hydrated mineral abundance to know where to extract these things via drilling for future crewed missions.
Now, ChemCam, which will be mounted on the robotic arm, will analyze the chemical and mineralogical composition of nearby rocks and soils that have ISRU potential.
Now we will take a look at the Radiation Assessment Detector, also called RAD. RAD will help us measure all the strong radiation signatures on the Martian surface. With this, we will be able to determine the effects of radiation on future Mars explorers.
The purpose of the robotic arm is to support and facilitate analysis on ChemCam as it analyzes the geological features of places that are hard for the rover itself to reach.
TAGSAM is a touch-and-go analyzer that will collect samples of subsurface ice, water, and phyllosilicates, helping us gain an understanding of the underground composition of Mars. This was actually inspired by the TAGSAM on the OSIRIS-REx mission, which served the same purpose but on an asteroid.
Now we will talk about PanCam. This instrument was aboard the ExoMars rover, and it will now be used by the Valor and Venture spacecrafts. This instrument takes panoramic color images of the Martian terrain, sun, and sky. With this instrument, we will be able to map out and find potential landing sites for future crewed missions.
The purpose for this instrument is to measure atmospheric pressure, temperature, humidity, winds, and ultraviolet radiation levels to detect storms and possible harmful weather.
Now to the next instrument, the Sample Analysis at Mars, also called SAM. This instrument was on board the Curiosity rover, and it will now be used by the Venture spacecraft. This instrument identifies a wide range of carbon-containing compounds, which can be used for future crewed missions to Mars.
But what good are instruments without locations at which to use them? Here you see a map of our entire mission. Structured over a 2-year time period, Venture and Valor will start their mission in the landing ellipse pictured in yellow to the right. After visiting 8 nearby locations in the primary missions, more about that later, the rover and helicopter duo will visit 3 secondary mission sites, pictured in blue, orange, and pink. The final scheduled research location is the tertiary mission, which is in green to the far left of the map. If we travel down to the primary mission, we can pinpoint where exactly the rover will visit. The red X represents the spot where Valor and Venture will touch down on the surface of Mars, after which they'll follow the dashed blue traverse path. On the map, orange indicates a high priority site, pink represents medium priority, and blue represents low priority. The acronym ROI above the orange site stands for Region of Interest, and it means the rover will spend additional time at those sites running further analyses. But first off, let's go a little more in depth on the primary mission. We classified these 2 sites as high priority because of the large concentration of water ice suspected to be present in those areas. Each location will be investigating using 3 instruments: TAGSAM to collect samples, ChemCam for comprehensive imagery, and Adrian-RM for water ice analysis.
Okay, so now we're going to move on to medium priority sites, which we're going to measure using the instrument ChemCam, and the potential value would be the carbonate, olivine, iron, and sulfate located in these regions. Now moving on to the low priority sites, which we're going to be observing using the PanCam, and the potential value would just be surface imagery of potential ice, including either surface or maybe subsurface ice. Now, moving on to the calculations for the primary sites. So we mostly calculated for speed and time, and this data collected, we used Perseverance and Curiosity data to actually choose our speeds. And as you can see from this first table, the first column is distance, second column is difficulty depending on the terrain type, which is the third column. Speed is our fourth column. Fifth column is the time actually calculated. And then the last column is going to be our classification. And this is the traverse calculations part 2. This is the same setup, just with different distances.
And here's our secondary mission. For Site 9, we'll be using ChemCam and TAGSAM on the Valor Rover, and we can find hydrated silica and silicon here. The terrain is known as a rock-strewn plain. And for Site 10, we'll be using ChemCam on the Valor Rover. Here we could find calcium, magnesium, iron, and pyroxene. And the terrain is known as a smooth plain. And for Site 11, we'll be using PanCam on Valor. Here we could find phyllosilicates, silicon, and clay.
And finally, we have the tertiary mission. A primary concern for crewed missions on Mars is the harmful effects of radiation on the human body. One possible solution is the utilization of lava tubes under the Martian surface for human habitation. In the green ellipse on this picture, you can see a darkened line in the rock. This is suspected to be a collapsed lava tube, and scientists expect there to be more non-collapsed lava tubes in the nearby vicinity. So, after completing the primary and secondary missions, Venture and Valor will travel over to these lava tubes. Valor will analyze the radiation levels and sediment makeup of the collapsed tube, while Venture will find a nearby uncollapsed tube and fly in it to explore and analyze the radiation levels.
And now on to the mission's possible next steps.
So you might be wondering where another site would be for a subsequent mission on Mars. Well, one of the sites we chose was the Nili Fossate. The Nili Fossate consists of faults up to 500 meters deep. We chose this site because it is known to be rich in olivine minerals.
Now moving on to future crewed missions. So what are the next steps that we need to take for an actual crewed mission? Well, it includes many factors, including infrastructure, energy source, transportation to and from Mars, agriculture, communication, waste disposal, and better spacesuits.
Now, we will reflect on our challenges, highlights, and experiences from the SEAS internship.
I went into this program with nearly no prior knowledge of space, and I got to learn about what NASA's doing to get people on Mars and the composition of the red planet.
Now, for my reflection, I loved being able to not only learn about Mars, but apply the information and research to an actual rover mission scenario.
I came into this without knowing too much about Mars. I'm happy that I was able to work with an amazing team to create a mission to Mars and create an experience that I will never forget.
Ever since watching a documentary about the Spirit and Opportunity rovers, I've always wondered what it would be like to design a rover mission from the ground up. The SEAS program gave me a chance to do just that, and on top of it all, I got to work with an absolutely incredible team.
I really enjoyed the SEAS internship experience because it taught me to work as a team, and I also learned more about Mars than ever before.
As an intern, I got to step into the shoes of a real scientist and conduct research using real-world data that can impact our understanding of Mars. I'll forever appreciate the SEAS program and the impact that it had on my career ambitions.
And now a big thank you to our mentor, S.J. Ralston. You helped us so much, and we wouldn't be able to do this without you. Thank you so much.
On behalf of the Mars Rover Resource Utilization Team, I would like to thank the SEAS program, Texas Space Grant Consortium, and NASA. Thank you for listening to our presentation. Are there any questions at this time?
So we invite the team to please turn on their cameras and unmute their mics. So the first question is, what was the most unexpected resource needed for a successful ISRU?
I can take this one. So the most unexpected resource that we found on Mars was sulfates because of the vast utilization possibilities. We could use it for a lot of things for future crewed missions on Mars, especially construction and propellant.
And how did you choose instruments that haven't yet been used on Mars, like TAG-SAM?
I can take this question. So we did a lot of research using the instruments that were sent to Mars on past rovers, like the ExoMars rover, like Curiosity, Perseverance, and none of them really targeted underground ice, retrieving that water underground. So we had to look beyond the box and try to find some solutions. And so when we came across the OSIRIS-REx mission that used TAG-SAM to kind of just touch and go on the asteroid Bennu, we saw that it was very successful. And so we're incorporating it into our rover to kind of be like a trial to see if it works. And if it does, in the future, we can send another robot, not just a rover, that's specifically focused on targeting underground ice, and maybe use something even more advanced than TAG-SAM, like a longer or deeper drill that can go in and collect more samples to be used for ISRU.
And how did you choose the minerals that you focused on for your mission?
I can go ahead and take that. We chose specific minerals depending on our goals. So at the beginning, before we even decided on like really sites or anything, we decided to actually create a list of our goals, which was including actually creating a mission that would actually prepare for future crewed missions, which is why we focus so much on either building materials or water. And then we actually put that on a graph, and we scaled every site that we were looking into and then chose which one was more important. And then the minerals that were actually needed to complete those actual objectives that we were looking for.
So does anyone on the team have thoughts on how you might reinforce lava tubes for habitation?
I can take this question. So the lava tubes are part of the tertiary mission, and we would explore them using our helicopter. And we haven't really done much research into how to support them or have a habitat inside them. But part of that tertiary mission would be sending the helicopter down to take pictures of the lava tubes so scientists back on Earth analyze them and come up with a more in-depth analysis and response.
So what was the one thing that surprised you the most in this project?
I can take this one. I think what surprised us the most was when us on the Traverse team had to use these different types of apps and data systems that we had never seen before, and we struggled with it at first, but near the end we got help from our mentor at Jay, and we got through it.
Great. So thank you all for your research, and I appreciate all of your wise answers to our questions. And we are ready for our next team, which is the Mars Exploration Team. The Mars Exploration Team investigated the infrastructure on the Mars planet's surface that is necessary to sustain the first cruise. This includes power, habitation, water, food, health maintenance, mobility, emergency care, and scientific support. Using basic engineering design principles, Interns designed a Mars village that will allow people to live and work productively and safely for up to 1,000 days on the Martian surface. A special thank you to Dr. Hum Mandel and Adam Noakes for their guidance and commitment to the Mars Exploration Team. Please join me in welcoming the ARA-1 long-term habitation of the Red Planet team.
Hello, we are the NASA SEAS Mars Exploration Team for 2022, and over the course of the past 2 weeks, we've researched and designed a Martian mission and base for sustained habitability on the Red Planet, which we are honored to share with you today. This is ARA-1.
Hello, I'm Abigail Heineman.
My name is Brogan Kirsch.
Hi, my name is Harper Clements.
Hello, I'm Maeve McCosh.
Hello, I'm Niles Alexis.
Hi, my name is Peyton Kelly Van Domlin. These are our mentors for the project, Mr. Adam Noakes and Dr. Hum Mandel. We are extremely grateful to them for guiding us along the way and being amazing resources for us to learn from.
The second closest planet to Earth, Mars has captivated astronomers for centuries. On July 20th, 1976, the Viking 1 lander took the first picture of Mars from the surface. We saw striking similarities between the Red Planet and our own. From colossal mountains and canyons to dry riverbeds that appear to have once contained water, Mars could contain evidence of life locked inside of its ice sheets, hidden beneath the surface.
The objective of our mission is to create a sustainable, affordable, and livable platform for human habitation on Mars through the use of the latest technology. Utilizing advanced material science and computer-automated design in an effort to refine and improve our ability to design, we've been able to create an extraterrestrial base that will allow a crew of 7 and an emergency crew of 14 to reside on the surface of Mars for 800 days. In an effort to create our base, we encountered various design challenges. This includes the harsh Martian environment, the general lack of local resources, as well as the time constraints of the mission itself. Each day as the sun rises above the Martian horizon, the surface is bathed in radiation, as much as 40 to 15 times more than Earth. This results in a need for radiation shielding for anyone who wants to safely travel and stay on the surface of Mars. In addition to radiation, the Martian regolith contains perchlorates. This makes contact with the soil, as well as anything grown in it, hazardous to human health. While Mars does have an atmosphere, it is only 1% of the pressure of Earth's, making it close to a vacuum. Not only this, but the vast majority of the composition of the atmosphere is carbon dioxide, necessitating a pressurized living space. To cope with the space and the weight requirements, the use of an inflatable hab will require the ability of the structure to maintain shape while both pressurized and unpressurized. The use of external structural support allows this to be achieved. Despite all of these challenges, the Mars environment isn't our only adversary. The mission requirements, including time, space, weight, and other factors, were all challenges to overcome. To meet these requirements, as aforementioned, an inflatable base design was used. Finding material that could withstand the pressure and block radiation was not easy. We eventually settled on PMMA, or polymethyl methacrylate double layer, with graphene sandwiched between as the base material, coated in Teflon, Dacron, and nylon. This provides a good mixture of tear resistance, strength, and radiation protection.
The following slides show the steps to our design process. Before coming on site, we split into research teams to ensure we understood all aspects of our projects so that we could immediately dive into brainstorming in person. We had the outer team who looked at base designs, how we would supply power, the environmental factors we needed to consider, and how we would communicate. The inner research team, which focused on the inner components of the project, with a focus on eclipse and other systems to support life, such as further water processing and greenhouses. And lastly, our humanitarian researchers, who looked at mental and physical health factors, what medical systems we would need, and the best foods to bring and grow. We later applied this research in the next steps of our design process. To get our base to Mars required us to structure the design to be easily compactable while still retaining its structural integrity. Our original plan relied on 5 SLS rockets carrying condensed components of the base. We determined that our compact base had a total volume of approximately 88.63 cubic meters, which we've estimated to weigh 22 metric tons using the ESM equation. This meant that considering the addition of life support systems and other resources being transported, we were able to eliminate 2 rockets with a final proposal of 3 SLS rockets to allow a lander to be transported alongside our base.
The base of ARA-1 is made up of 5 primary general habitation structures, or GHS, interconnected by 3 dual advanced inflatable airlocks, or DAIA. They are arranged in a way to optimize space while allowing for redundancy, as each GHS is connected to at least 1 airlock, specifically the DAIA. This layout allows for a depressurization event to occur in any individual GHS or module without collapsing the entire base, and ensures that if an astronaut is in a GHS during depressurization, they're able to escape back into safety. We structured the base to have multiple external ports on each module. This is to allow for expansion of the base and further missions as a result of the design's modularity. The structure of the base can be modified and adapted to fit various terrain obstacles in order to create a much larger base as time goes on and further missions are conducted due to this modularity. Each GHS is composed of an inflatable structure, 3 ports, and a support system. The inflatable structure is attached to the supports via the skylight at the top center of the base. The inflatable is the main habitation area for the astronauts and has a radiation shielding and insulation, but still remains flexible to allow for its inflation. The structural supports extend 3 ways down from the skylight, and the base attaches to them along the surface of the inflatable during expansion. The structure reduces stress on the inflatable and also prevents structural collapse in the event of the base's depressurization. The supports are telescopic and can extend during deployment in order to reduce the space they take up during shipment. The skylight is an oblong dome-shaped structure on top of the base that allows 1 to 2 people to sit inside and look across the Martian surface outside of the base. This structure allows astronauts not only to visibly see outside conditions and changes, but will greatly help mental health, as an alien world such as Mars will be an amazing thing to see. The 3 ports are either oriented with one opposing the bisection of the other 2, which are at a 60-degree angle to one another, or are equally spaced around the GHS, bisecting each support. This is the model shown here. These 2 port layouts allow for GHS structures to function both as corners to an equilateral triangle, as well as center points or extensions to the primary shape of the base, such as in the exploration module, or what's shown in front of you. The versatility of these 2 layouts is what allows our base to expand around terrain hazards for further missions to the base, and is a key component in the modularity of the base. The DIA, or DAIA, are dual airlocks that allow for compact shipping, modularity, and streamlined deployment. They are composed of a central metallic structure that allows for storage en route to Mars, as well as a place to attach other modules through a port on either side, and a port on each end. The inflatable aspect of the base are 2 accordion-like inflatable structures interconnecting each side of the DIA to its center, as is shown in front of you. After the first extension, the inflatable portions of the DIA will be reinforced with support rods stored within the DIA while it's still collapsed, in order to preserve their shape during depressurization, which will occur if the DIA ever needs to be used as an airlock. Each module has its own deployment system, every module interacting with the next. The GHS will deploy to the surface of Mars in a few primary steps. They will begin compressed for flight, as is shown here. They will then be lifted by a rover present at the landing site and fold outward. This is also shown. From there, the supports will telescopically extend, allowing the base to stand on its own without rover support. The base will then finally partially inflate to allow for easy attachment to the DIA modules. The DIA will fully inflate, as is shown, to allow for connection to the GHS. The partially inflated GHS will be able to contour based on where the ports are moved. This will allow for astronauts to easily attach the GHS and DIA together once they arrive.
To aid in the design and development of our base, we utilized 3D design software. Specifically, we used Autodesk Fusion 360. Through the use of iterative design, we were able to model the exterior of our base and our crew quarters. Integrating our design into Fusion 360 allowed us to use features such as its advanced design tools and rendering tools to create realistic renditions of our exterior and sections of the interior of our base. Starting with the main inflatable module, I proceeded to create the skylight as well as the external support beams, primarily responsible for the shapekeeping and support of the base. After this, we created the preliminary inter-hab tunnel design and eventually added support legs. Finally, we created a design with all habs fully integrated and connected in the final triangular 4-hab configuration. One major constraint of the software was not necessarily the feature set, but the computing power that we had access to.
Mars has an atmospheric volume of less than 1% of Earth's, thus allowing over 250 millisieverts per year to reach the surface. Therefore, any Martian base would need to absorb or block a large majority of the excess radiation to protect the health of the astronauts. Due to the compact and lightweight nature of inflatable structures, the team wanted to find a material which could be woven into or placed between the layers of fabric in our inflatable structure without adding too much extra mass or rigidity. With these parameters in mind, the team discovered that graphene, a single atom-thick sheet of carbon, absorbs 98% of the solar radiation, and furthermore, perfect graphene can withstand 14 million pounds per square inch, which would also aid in creating a pressurized base without the risk of breaking the seal.
After designing our external base, we turned to focus on each component we included and any support systems needed to sustain life in our habitat. The base is split into 5 modules, A through E. As mentioned previously when discussing the external structure for our base, each module will have external supports and doors that connect them to the partial airlock hallways. The design of the base is structured to prevent total depressurization, instead allowing the event to be limited to one module without damaging mobility between the other functioning rooms. Module A will be used as utility storage facility for a majority of the extra supplies and will house the main of our 2 ECLS systems. Module B will house our lab, including workstations for all research projects planned for Mars. Module C houses the sleeping quarters of the R1 base, with added storage areas that can be converted to sleeping quarters in the event the base needs to support life for 14 astronauts instead of the planned 7 for the mission. The pod-style living areas will allow individual spaces for each astronaut, while being large enough for movement and comfortable enough for sleep. Module D is our central module, which connects to all hallway airlock systems, allowing for access to any component of the base in the event of depressurization. The centralization of the module creates the ideal environment for our base's exercise, eating, kitchen, and meeting areas.
Environmental control and life support systems, or ECLIS for short, is a crucial factor in any space mission. The functions of ECLIS are as follows: providing and recycling oxygen for metabolic consumption, providing and recycling water for consumption, food preparation, and hygiene uses, removing carbon dioxide from the cabin air and filtering out particulates, microorganisms, and volatile gases, and maintaining total cabin pressure, temperature, and humidity levels. Our ECLIS systems will be largely based off of the ones used on the International Space Station, or ISS. For water recycling, a Paragon urine processor and a water processor assembly will be used. All wastewater eventually ends up in the water processor, where gas and solid materials are removed and the water is filtered multiple times. The steps for oxygen recycling are as follows. An oxygen generation assembly electrolyzes water provided by the water recovery system, which creates oxygen and hydrogen. The hydrogen is vented out of the habitat or spacecraft, and the oxygen is delivered back into the air.
Using the ECLIS system on the ISS as our base model, we were able to determine the efficiency of each component for sustained habitation. Further research showed issues which we would need to fix in order to support life on Mars. On the left-hand side of the slide, we can see the projected efficiencies for a commercial ECLIS system on Mars, which includes the following adaptations to the ISS system as tested by the 50th International Conference on Environmental Systems. Replacing the current OGA system, which has been proven inefficient even for the ISS, with a new oxygen processing system of OPA designed by Gyno Labs in partnership with NASA. We will shift from the current carbon dioxide removal system to the carbon dioxide removal ionic liquid sorbent system, which eliminates the need for the CMS system. The replacement of the urine processing assembly with the Paragon urine processor, and finally the replacement of the current ISS CRS system with a more efficient PCI microlith-based Saboteur reactor system. Again shown in the chart, running this improved ECLIS system at the same oxygen and water recovery will yield more efficient results than the ISS gains, which allows our base to increase both oxygen and water recovery.
In 2012, the Curiosity rover discovered the presence of a variety of elements, including nitrogen, phosphorus, and potassium in Martian regolith. These essential nutrients, also found in soil here on Earth, contribute to the overall health of a plant, in addition to its nutritional value and just general ability to grow. Additionally, while the decreased atmosphere on Mars should have no effect on the height of a plant, the reduced gravity environment will increase the rate of respiration, resulting in an elevated growth rate. Also, as long as sufficient light is provided, the roots of the plant will continue to grow away from the light source, allowing us to adequately water the roots of a plant in decreased or zero gravity.
After discussing the methods of growing plants in our base, particularly through the potential addition of a greenhouse module, we decided that the most efficient solution would be to utilize the space we already had within the hallways. This new design allowed us to optimize space we already had, use the UV lights involved in the growing process as hallways lights, saving power and taking advantage of the airlock design to protect the plants in the event of a depressurization. Additionally, we decided some of the chosen plants for our base could be grown on ceiling systems that were able to be hung over the hallways, again maximizing space and minimizing power cost.
Something that we still needed to figure out, though, was the method of growing food on Mars. We could grow the plants in Martian soil or even sand, but that could get messy, and particles could contaminate the air or cause issues with filtering systems. Hydroponics, or growing plants in water instead of soil, seemed like a good option. Plants tend to grow faster and larger in hydroponic systems as opposed to regular soil. In addition, hydroponic systems are not as labor-intensive and require less maintenance. However, water also poses the problem of interfering with technology if it spills. Other potential complications of hydroponics, such as mold and algae growth, nutrient deficiency, and plant diseases, pushed us to consider different options. We discovered aeroponics, which is a method of plant growth in which no growing medium is involved. The plants are grown in a closed or semi-closed environment of air and mist. This method is more successful in preventing plant disease, and it provides the roots with more oxygen, which is beneficial. Aeroponic systems also require very little maintenance. However, aeroponics would be quite expensive. Another major problem is the fact that an aeroponic system depends on electricity for automatic misting and fog. If the roots are not misted frequently, they will dry out. This means that a power outage for even just a few hours could result in the loss of all of our crops. In the end, our method of plant growth remains undecided. Each approach has several benefits as compared to the others, but none of them come without significant drawbacks. Further research and experimentation will aid the decision as we continue to make new improvements and innovations.
Communication on Mars is something that is very hard to test because we don't have people on Mars. That said, we devised a strategy that would hopefully make communication on the Martian surface, as well as with Earth, relatively simple. The first point is surface communication and location tracking on the Martian surface. We discussed placing one satellite around the equator of Mars and then decided against it due to how it limits where you can place the base. We continued our research and found that having 3 triangulated satellites would be best for both GPS tracking and for communication. The reason for this is by having 3 satellites, the astronauts have more terrain they can explore without losing connection to the base. It also guarantees a more precise location tracking system, which makes it easier to navigate the surface of Mars. These satellites could also be used to take more photos of Mars and the base. The way these satellites would work is there would be either antennas or receiver dishes situated at the base and on top of rovers. In a similar way to how wireless communication and GPS tracking works on Earth, it would work the same way on Mars. We then discussed communication between Earth and Mars. We agreed we could use large antennas to communicate between the 2 planets. These ideas were inspired by how we currently receive signals from the rovers already on Mars, such as Curiosity or Perseverance. The one difficult aspect of communicating with Earth from Mars is that communication time varies based on the position of both planets and can be anywhere from 4 minutes to 20-minute delays. The longest communication delay that will ever occur in human space travel is between Earth and Mars. And because of this, we also felt that there could be of use to have a potential relay satellite between Earth and Mars so that you can have stronger communication signals and potentially reduce some time during those longer delay periods.
Any mission into space poses health risks for the astronauts involved. But the length of this mission, which is over double the longest consecutive amount of time any human has spent in space, in addition to the distance traveled, could result in more extensive health risks. Experts say astronauts may lose up to 22% of both density, in addition to a decrease in eyesight, blood pressure, and muscle mass. Additionally, as previously discussed, the thin Martian atmosphere exposes astronauts to 40 to 50 times more radiation than on Earth, posing a greater risk of cancer and potentially radiation poisoning. Luckily, from our decade of research aboard the ISS, many mediation methods already exist to help keep the astronauts healthy. In addition to preventative measures, such as the use of graphene to absorb radiation and daily exercise of over 2 hours to keep and build muscle mass, the astronauts will also have access to medications such as calcium supplements, vitamin D, and other multivitamins to maintain a healthy balance of all nutrients. It is also important that our astronauts maintain a healthy, balanced diet and drink enough water throughout the duration of the mission. The days, or sols on Mars, are roughly 40 minutes longer than the days here on Earth, which could disrupt and desynchronize the astronauts' circadian rhythm, resulting in sleep loss, fatigue, headaches, and more. To ensure our astronauts are fully acclimated to the Martian day, light therapy will be used, simulating night and day, on the transport both when traveling to Mars and on the return flight.
The long-duration isolation with few other humans, limited contact with loved ones on Earth, and the sheer distance from home will have significant effects on the astronauts' mental health. Long-term, astronauts can become unhappy, unmotivated, anxious, and depressed if their mental health is not cared for. Aside from the obvious negative impact on the astronauts, lack of motivation will have a harmful effect on the mission itself as well, as mission objectives may not be met. This is one of the reasons why we prioritized mental health as a main factor in planning the RO1 mission. If the astronauts are not functional, the mission won't be either. Crewmates will be encouraged to bond and socialize with each other through frequent game nights, movie nights, and other fun activities, as well as eating meals together. During their training on Earth, astronauts will learn techniques such as mindful breathing, journaling, and other self-care methods to combat problems such as anxiety and depression. Each crew member will also be required to go through a brief training in psychology so that they can emotionally support and guide their teammates should mental health problems arise.
To determine the number of launches necessary to transport all of the equipment to Mars, we did a full cost, power, and weight analysis of any material that would be important for this mission. This spreadsheet also helped us gauge which electrical systems could be running concurrently, in addition to the total cost of the mission. As you can see, the total cost of RO1 is just over $1 billion, way less than our $5 billion requirement maximum. The total weight of all materials being brought is around 70,000 kilograms, which translates to 4 SLS rockets for equipment alone. And out of 40,000 watts available from the 2 primary nuclear reactors, we only plan to use around 33,500 watts, with all of our electrical devices running concurrently.
To keep the base powered, we've utilized the kilopower nuclear electricity production system. Our system consists of an array of 3 nuclear reactors. Each nuclear reactor weighs 1,500 kilograms and produces 10 kilowatts. The third nuclear reactor is for use in emergency situations, as the base only requires 20 kilowatts to function normally. The reactor core is made from a uranium-235 molybdenum-99 alloy, which utilizes a boron carbide control rod to control the nuclear reaction and keep it stable. The reactor produces heat which is carried by copper pipes to the Stirling power conversion system. To dissipate excess heat, an array of radiators is mounted at the top. To reduce radiation exposure to the crew and protect against potential damage, the core and Stirling power conversion systems will be buried underground, with only the radiators showing. This reduces weight and cost, as additional shielding is not necessary since the reactors will be underground.
As a group, we decided to take our sketches and our 3D rendering and turn it into a 3D print. This meant scaling it down and making something far more simple so that the printer could easily print it in a short period of time. We started this process by creating a sketch to align where everything would go. We then created an actual 3D model on top of this sketch, which had all the pieces connected. We then took these pieces and broke them down into 2 smaller pieces so that we could print it on separate printers at the same time, because if we had printed the whole thing together, it would have been a 12-hour print or more. We had these 2 separate pieces, one being a 7-hour print and one being a 4-hour print, and we printed them as many times as needed. Unfortunately, some of the prints failed overnight due to technical error, and we didn't have time to reprint them due to time constraints. We wish to someday print them again and make this model the way we had intended to.
SEAS was an incredible opportunity to work on a subject that I am passionate about with a team of like-minded people and learn from amazing, helpful mentors.
SEAS gave us the chance to learn more about space and other STEM fields in an environment where we could include both our creativity and scientific skills.
We'd like to thank NASA, NASA SEAS, the Texas Space Grant Consortium, and the University of Texas at Austin Center for Space Research for providing us with this amazing opportunity. We are especially grateful to our mentors, Dr. Hum Mandel and Mr. Adam Noakes. Finally, we'd like to thank Ms. Margaret Baggio, Ms. Selena Miller, and the rest of the SEAS crew for supporting us and helping us along the way.
Really interesting project. I want to invite all the team members to please turn on their cameras and unmute their mics. We have several questions for you. The first question is, how long did you spend in your brainstorming and concept design compared to the amount of time it took for your CAD building and 3D printing model? Is there anyone that wants to answer?
I can take that one. So we started with our brainstorming the first couple of days and made our final base what we wanted it to look like. And then a couple of us split off and started with the CAD design while the rest of us brainstormed our internal design. That way we were able to get both external and internal parts of the base while also having our CAD designs that you've seen in our presentation.
And what was the biggest lesson you learned in working together?
I personally think the biggest thing we all learned as a group was how to take a bunch of different ideas that we were all working on, because obviously there's a bunch of tiny little things that go into making an overall base, and how to mix them together in a way that works. You know, I think that was the biggest thing, and just how that applies to other teamwork scenarios.
Did you have an opportunity to work with the other the Mars Utilization team to bounce ideas off of?
We actually worked more closely with the Moon Habitation group because they were facing a lot of the same challenges that we were. So focusing on protecting the health of the astronauts, looking at radiation in terms of the astronauts, and building a physical base.
Did you consider how you might treat Martian regolith to remove things that could be toxic to plants?
So a lot of what we looked at with our greenhouse system and all of that was actually using Mars soil, because we wanted to use both hydroponics and aeroponics. So we did look into what nutrients we would need to add and what we'd need to take out in order to actually sustain plants.
And how did you know what to include inside each of your modules?
We focused mainly on what we wouldn't be able to bring. So we only brought items that would be essential to the mission. So lab materials were a priority, food, equipment for packaging food and making food to fit within our cost, power, and weight restraints.
And how many of you actually had CAD experience prior to this project? And how important was that skill in your habitat design?
A few of us have had CAD experience before, but in my opinion, I've had a pretty significant amount of CAD experience, and I'd say that played a really significant role in the design of our project.
Great.
And
Well, you
then-
did it. Yes.
And then I'd taken a class on it previously, so I wasn't as good at the computer rendering, but I had done a lot of 3D printing. So we did actually, like I said in the video, make a 3D print attempt, and it did come out. It's just the printer didn't make it look quite how we wanted, so we didn't show it. But that was like the experience that we had and how we turned it into something like that.
Great.
I also had some CAD experience with 3D printing, kind of like Harper, a lot less on the computer rendering side, but I did design a lot of 3D prints. And so we actually had multiple people working on the CAD rendering and the 3D printing.
Well, you did an excellent job and I learned a lot, and I think your design is very interesting. So thank you all for joining us today, and thank you for sharing your research. So we're going to take about a 20-minute break. We invite you to watch highlights of the student accomplishments during the Earth and Space Science course and the Python course that the students took prior to their actual project. A special thanks to Teresa Howard and Asha Carmacher for scoring and preparing these highlights. We want to remind all of the interns that they will receive their certificates for each module that was completed sometime before next week. So you can watch for those. They will be sent to you virtually. We will continue our presentations today at 4 o'clock.
Yes.
Question forgot. I know budget.
So welcome back to our SEAS presentations. Our next group is the Asteroid Photometry project that was guided by Tom Rutherford. He's an astronomy adjunct professor at East Tennessee State University and King University, and he provides its students the opportunity to investigate and understand asteroids. Our thanks to him for his guidance and commitment to the SEAS interns. So please join me in welcoming the Asteroid Photometry Project Photometric Analysis of Asteroid 14691 team.
As a simple definition, asteroids are rocky objects that did not accumulate into larger bodies. They're kind of like the leftover material in the solar system that didn't combine to form a planet. They're not the destroyed remains of a former planet, they just never formed anything larger. Some asteroids even have smaller asteroid moons orbiting them. most asteroids orbit the Sun between the paths of Mars and Jupiter, the main asteroid belt, although some are found in other areas. A Lagrange point is an area of space that is gravitationally stable, where forces are balanced. James Webb orbits the Sun at Earth's second Lagrange point in its halo orbit. Trojan asteroids orbit in Jupiter's Lagrange points, but Jupiter, with its large mass and subsequent gravitational influence, it creates gaps known as Kirkwood gaps in the asteroid belt where asteroids cannot orbit. However, there are some asteroids that do have highly elliptical orbits and pass through the inner solar system. An example of this could be the Apollo asteroids, which cross the Earth's orbit. We visited asteroids for multiple purposes, whether as targeted missions, such as JAXA's Hayabusa probe, or Galileo on its way to Jupiter, passing 951 Gaspra and 243 Ida, which has a small moon named Dactyl. Asteroids can be made of a variety of materials. Of course, there's 16 Psyche, a rich metal asteroid of great material worth by human standards, but actually there are three more broad classes. 75% of known asteroids are C-type carbonaceous asteroids, 17% are silicaceous, S-type, and the final 8% are metallic, M-type. But the wide variety of this composition is important to us as scientists. We want to understand our origins within our solar system, and by studying asteroids, we get this key insight about what this solar system looked like 4.5 billion years ago. Asteroids are the fundamental building blocks of the solar system, providing essential insights to understanding not only the system's formation, but the formation of Earth and the foundations of life itself. The asteroid we studied in this project is able to be identified by its number, 14691. It was selected using the Minor Planet Info Observations target search and was selected based on its location, whether it would be near opposition, at, or near the time of data collection. For reference, when an asteroid is at opposition, it means that the Earth is exactly between it and the Sun. From there, the JPL Small Body Browser allowed the determination of the asteroid's coordinates on nights where time was available.
The main goals of this project were to determine the shape, rotation, composition, and distance of the asteroid. These goals were successfully met using astronomical image processing software and empirical methods of data collection.
The image sequences for this asteroid came from the Southeastern Association for Research in Astronomy, or SARA, and more specifically, the SARA CT and SARA RM telescopes. Just to give a brief background on these instruments, SARA CT is a 0.6 meter telescope located in Chile, and SARA RM is a 1 meter telescope located on the Canary Islands. Our asteroid data was collected during the months of April and May, with each data set recorded within a span of a day. The majority of the images collected from the telescopes were calibrated. This means that frames were used, bias, flats, and dark frames, to remove any noise, vignetting, or dust in the optical setup. To perform the photometry on this data, the software Astro Image J was used.
Photometry has to do with the measurement of the amount of light within an aperture of a fixed size, measurement of the brightness of stars or other objects, like the asteroid we're studying in this project. It's normally done through the usage of filters, where you're subtracting color and filtering out different wavelengths of light. What we're trying to do is figure out the brightness of the asteroid as it can be seen in the sky, and by using a comparison star of a known fixed magnitude or brightness, we're able to determine that accurately.
After loading in the dataset, we simply located the asteroid and used the comparison star to generate a magnitude for the asteroid. For each dataset, we equally divided the magnitude amongst our team and compiled it into a table, along with the Julian date for each image. To further collect data on the specific shape of the asteroid, we were assigned to create models. Collectively, we decided that potatoes would be a great model, as their varying elongations could help us assess a potential shape for our asteroid. We also modeled styrofoam into different shapes to achieve the same feat. I'm going to hand it over to Pablo to talk a little bit more in depth about our asteroid modeling.
Using layered styrofoam, I was able to cut out and mold an approximate shape of our asteroid. I then painted a wooden stick and created a floating platform for the asteroid model. Using a green screen, I was able to shoot a sequence of 16 images, rotating the asteroid on its 3 axes for a full rotation. From there, I composited the images in Photoshop, removing the green screen and putting a generic starfield image to simulate an asteroid in space. Heading over to AstroImage-J, I performed photometric practices that we learned and applied them to this model, which resulted in a light curve depicting my model asteroid over an arbitrary period of amount of time. Here's a GIF of my model asteroid tumbling through space. Our asteroid actually has more of an oblong, elliptical shape, so a potato seemed more like a better option to model. Using a drill, Rajveer attempted to spin his model asteroid. However, we were unable to successfully use a potato for a model. After this, we created a graphical representation of our actual datasets, including the asteroid's real shifting magnitude and variable rotation rates. The first graph depicts the asteroid's magnitude versus Julian day on the night of May 21st this year. Through analyzing trough to trough and peak to peak, we found the rotation rate was 0.50 Julian days, or about 4 hours. On the night of May 17th, we found the asteroid's average rotation rate to be 0.150 Julian days, or just over 3.5 hours. Something to note is the noticeable shift in values near this peak, which was actually due to the asteroid passing over a background star, ultimately shifting its true magnitude. On the night of April the 20th, we found the rotation rate to be 0.15392 Julian days, or just over 3 hours and 40 minutes. With careful analysis, we averaged the rotation rate from May 17th, 3.61, and April the 20th, 3.69. This averaged to a rotation rate of 3.65 hours, which lies in conjunction with the self-reported rotation rate of 3.6524 hours from the asteroid's original discoverers. It was a near-perfect match. Finally, we individually created graphs using color-filtered data from May 17th, as seen here. The BV color index was plotted against the V magnitude of the asteroid per common practice in observational astronomy.
Our final goal was to understand the distance of the asteroid from Earth. In order to do this, we needed to calculate the parallax near the time of opposition. But what exactly is parallax? Parallax is defined as the apparent displacement of an astronomical object as a result of the change in the observer's point of view. Since we only tracked the asteroid with one telescope, we recorded the displacement of the asteroid over time in the X and Y planes between the two images, about 3 hours apart. After converting this displacement to degrees, we further calculated the displacement of the Earth's orbit between the time of the two images. Using this information, along with some trigonometry, a distance of 1.57 astronomical units between the Earth and the asteroid was calculated. We found that this value was close to a previously calculated Earth distance value of 1.584 astronomical units.
To calculate the parallax of our asteroid, we actually had to use a different method than what is normally used. This is because one of the telescopes we were supposed to use was in the middle of a blizzard. So this definitely emphasizes some of the challenges that come with ground-based telescopes. So in order to calculate the parallax, we had to use a different method than usual. Normally, parallax is determined using two telescopes and the asteroid. However, because we only had access to one telescope, we used said telescope and two different locations of the asteroid. As per usual, with many scientific observations, we ran into a few more challenges as well. One of the biggest challenges we encountered was determining the color index of the asteroid. We used two color filters, blue and green, to find the asteroid's color at various points in time. By doing this, we hoped to see whether the asteroid changed color. If our graph was unchanging, the asteroid's color would be unchanging as well. If the graph had curves or a nonlinear shape, we would know that the asteroid is changing color. Unfortunately, we ran into a bit of a challenge. For our first run, we divided up image analysis among the members of the team, each person getting about 6 images to analyze and record data for. We then compiled all of our analyses into one graph. However, when this graph was completed, the data points on it were scattered and didn't follow any visible pattern, as you can see here. So we tried a different approach. Instead of dividing the images among team members, each member analyzed the entire data set. Then we each made our own graph. However, this didn't turn out too well either. Each one of our graphs were totally different, and once again, none of them followed any kind of pattern that we were expecting, as you can see. Ultimately, we decided that it was possible that the asteroid was changing color, but there wasn't enough definitive evidence to make any concrete conclusions. In this case, we would need more data in order to be able to make a final accurate interpretation. So as you can see, we definitely encountered a few problems, but as our mentor likes to say, if you don't have to do it 3 or 4 times, you're doing it wrong.
Not inconclusive, it was interesting to see the way the graphs came out, and we had a good time trying to come up with reasons for why the data might have come out this way. but as was previously mentioned, we decided to move on to the next step of our project, which was modeling. A big highlight of our work ran into plenty of problems and had to revise our procedure for making the models many times. First, our plan was to put a potato on a drill and find the potato's light curve. But while doing that, we found that the drill spun too quickly and in some cases flung the potato off of it. After attempting it this way, we put the potato into a stand and moved the potato by hand, taking pictures between each movement. Though doing it this way took more time, our team enjoyed the process of working on the models. Another part of our work was the parallax. Instead of doing parallax the traditional way of 2 telescopes in the asteroid, we had 1 telescope with the asteroid in 2 different locations. When we first started working on the parallax, we were confused on how we would do this, but after getting some help from our mentor, we were able to better conceptualize how to do the parallax and get the data. And lastly, here are our individual relationships. I really enjoyed the opportunity to work with our mentor, Mr. Rutherford, throughout this past month, and I'm grateful for all he taught us throughout the program, including using new softwares, analyzing data, and the more conceptual stuff about astronomy. I had a great time working on this project and learning from my peers. This was an amazing internship experience.
I just want to say thank you to everyone who made this internship possible. I had a great time and learned a lot in the process. But I didn't just learn how to find the rotation rate of an asteroid or how to analyze image data using complex software. I learned what it means to be a good teammate. I'm really grateful for everything this program has to offer, and I look forward to using what I've learned in future endeavors.
I'd like to formally thank all institutional entities involved in the SEAS internship, including NASA, the Texas Space Grant Consortium, and the Center for Space Research. With their grants and support, the SEAS internship is able to foster young scientists and lend credibility to the importance of educating America's rising scientists. As an aspiring astrophysicist, this internship has strengthened the resources and skills that I need to successfully pursue this career, from creating a collaborative environment with my peers to independently meeting goals using intricate software. Similarly, this internship has given me the opportunity to be published in my local newspaper and network with regional Nevadan scientists in the Nevada Space Grant Consortium. I am most proud of our wonderful mentor, Mr. Rutherford, who has lent us his valuable time and helped us advance our abilities as rising scientists. I am also thankful for being part of such a vibrant team of people that want to create big changes in this world. With our engaging meetings and fun jokes, we've established a bond that will last past SEAS. Thanks again to everyone for this amazing opportunity. I'm proud of representing my community as a NASA SEAS intern, and I hope one of you watching this can say the same thing next year as well.
This internship was a one-of-a-kind experience where I've grown both as a person and a scientist. Firstly, I want to thank Mr. Rutherford for all he has taught us throughout the internship. We are truly grateful to have had such a knowledgeable and helpful mentor who always encouraged us to be resilient as a part of the scientific process. I also want to thank my fellow photometrists who have made this experience truly memorable. As an aspiring astrophysicist, this program has provided me with excellent research skills and has solidified my passion for exploring the universe. Whether it was creating and analyzing light curves or setting up a potato drill model for our asteroid, I've truly enjoyed my time in the NASA SEAS internship, and I will be sure to carry the lessons I've learned here to my future scientific endeavors.
This program was amazing, not only to have the opportunity to work with peers across the country and an amazing mentor, but also to learn more about Earth and space science, both through our assigned project and through all of the speakers that we learned from throughout the internship program. This is all we have for you today. A big thank you first to our mentor, Tom Rutherford. Without him, this project would not have been possible. Secondly, we'd like to recognize Sarah, the Southeastern Association for Research in Astronomy, for telescope access and time to collect data on our asteroid. Our sincerest thank you to the SEAS program for providing us the opportunity to connect with each other and together learn about the fields of Earth and space science and the opportunity to do some real science. And finally, to our audience, thank you so much for being here, and I think it's about time to open it up for any questions.
Very interesting, and I appreciate your research. We want to invite your team to please turn on their cameras and unmute your microphones. We have several questions for your group. The first question is, what did you learn about the scientific method and working with inconclusive data?
Sure. So it was a way to be able to step back and ask ourselves about our methods to make sure there weren't any more surface mistakes. A lot of times we were able to attribute some of the unexpected parts of our data to different events. Like in one of our rotation curves, we had our magnitudes a lot lower than we expected. And we noticed in our data set that the asteroid actually passed in front of a background star. So it was a way to check ourselves and see if there were any mistakes we personally made in our analysis of data, or just be able to attribute it to a lack of data itself and a need for more.
And what was your favorite part of the internship?
Our favorite part of the SEAS internship was getting to work together on all the different aspects of the project. So throughout the modeling phase and during data collection, we all kept in close contact with our group chat despite being virtual. And we shared laughs about modeling fails like the potato and the drill. And we worked together to try and understand the data.
Great. And why do you think that asteroid modeling is important?
So asteroid modeling is really important because it really helps us better understand an asteroid's profile, including its possible trajectory, both past and future, as well as it might be composed of something that we might not know about. Similarly, modeling an asteroid can help us better determine how and why its shape came to be.
And what is a Julian date?
So Julian dates represent actual dates in time. So we converted our actual date and time values from when our images were taken to Julian days in order to get a continuous timeline. So the problem with actual dates is that we have leap years, among other things. And Julian dates give us a simple and continuous timeline to make graphs and things. So Julian dates look like really big numbers, but it's really just the number of days elapsed from the starting point at January 1st, Universal Time, noon, 4713 BC.
And how difficult is it to get access to telescope data?
Yeah, so in general, it's actually not very difficult to get access to this type of data. For us, it was especially easy as our data came from our mentor, who has associations with the Southeastern Association for Research in Astronomy. And he was able to get telescope time to gather our data for our project. But data is also publicly available through NASA-affiliated organizations like JPL, which has, for example, the small body database lookup, as well as exoplanet databases.
And what did you feel was the most challenging part of your internship?
Yeah, so overall, we faced two main challenges with this project. One was a lack of data. So in order to do a more thorough job, ideally, we would need months or even years of data, as our mentor told us. But for this challenge, we just made do with what we had and did some pretty good analyses in the process. Another one of the challenges that we faced was general human error. So we made do with what we had, but we tried to be as accurate as possible and made sure to thoroughly understand the problem that we were trying to answer. So by doing this, we were able to look at the answer we got and ask, does this make sense? And if so, we continued with the analyses, and if not, we did, again, a different method to try to understand where we went wrong. So overall, these were pretty significant challenges, but we worked through them together as a team.
So looking ahead, how has your viewpoint of astronomy and studying asteroids changed?
So my viewpoint on asteroids and astronomy has changed because I've gained a more practical approach to these different concepts. We've been able to use Astro Image J to understand magnitude, and if we were able to, we were able to get the spectra and all the light curves from the asteroid that we used. And with this, I've been able to understand astronomy in the way that actual scientists do. And that makes me feel amazing because that's what I want to do in my future. And that was personally a really fantastic experience. So I'm really glad that analyzing something as small as an asteroid and not something big, we can still understand the many intricacies involved with space.
So kind of piggybacking off of that, up until the SEAS internship, I didn't really have a ton of exposure to the more mathematical side of astronomy. And so I really enjoyed getting to look at the numbers and the data behind what I want to study personally in the future. and getting to use all the programs such as AstroImageJ and then making graphs, they really helped me to understand what I want to do.
Also jumping in, it was really interesting to be able to study asteroids just because asteroids are kind of these fundamental building blocks of our solar system. And it's really interesting to be able to study them and see a really far back into the past, 4.5 billion years ago, to when our solar system was forming, and get key insights about where we came from as humans and as life on Earth.
Well, you've done an amazing job with your project. I know that being virtual is always a challenge, but it sounds like you've done an amazing job, and I can tell by your research you were successful. So I want to thank each of you for your time and your talents, and thanks for sharing your research today. So our next group is the interns in the Astronomy, Age, and Distance to a Globular Cluster project. And this group determined the age and distance to an open cluster of stars. Students used astronomy software to analyze the data collected and calculate the member stars' magnitudes. Our thanks to their project mentor, Olivia Cooper, for her leadership and commitment to this astronomy team. So please join me in welcoming the age and distance to a globular cluster team.
Hi everyone, my name is Krisha Patel.
I'm Arushi Gupta.
I'm Michael Fang.
I'm Grace Clement.
And I'm Raj Lachman.
Before we begin discussing the open cluster we researched, to start off, what is an open cluster? Held together by stars, open clusters are groups of stars with similar ages, compositions, and distances from Earth. These clusters develop when molecular clouds collapse, and there are thousands of stars in the cluster that are all extremely active. And this image on the slide is one example of an open cluster. Open clusters are essential for understanding star evolution because there are many relatively young stars. Stars from open clusters also form one giant molecular cloud, and since they have similar ages and compositions, it is easier for astronomers to determine properties using photometry, which we also use in our own research as well. Overall, open clusters aid in identifying the effects of variables on stellar properties and stellar evolutions.
The open cluster our project is focused on is NGC 1245, which was first discovered by William Herschel in 1786 and was previously studied back in 1964. NGC 1245 is part of the constellation Perseus and has over 500 members, in which our project culminates 461 of them. The data for this cluster was provided by the Roque de Muchachos Observatory of the Southeastern Association for Research in Astronomy, also known as SARA. Our targets for this project were divided into two categories, scientific and group goals. Our main scientific goal was to determine the age and distance to the open cluster NGC 1245, and our group goal was to collectively interpret a large data set of stellar magnitudes in both the blue and visual filters using AstroImageJ software. The outline of our project is divided into 5 main steps: determining the star numbering system and star division, photometry on AstroImageJ, correct values to account for reddening, graphing the data set to determine the turnoff point, to finally determine the age and distance.
So before we could do anything, we needed to determine a star numbering system to organize and identify stars, because as you can see, there's over 500 stars in NGC 1245, and we needed a way to organize them so we could know which star is which. And what we eventually did is we looked through a few star numbering systems, and we settled on one made by Guido Scincarini, who is an Italian astronomer. And you can see his star numbering system here, the one we used. Yeah, so next, photometry. Photometry is basically what we did our entire internship. It's the science of measuring light in relation to a observed brightness as opposed to the actual brightness of the star. So we used AstroImage-J, which is an astronomical image analysis software, to determine the magnitudes of target stars in NGC 1245 in relation to B and V filters. The magnitude of target stars is just their brightness. It's a measure of brightness. And we took their apparent magnitude, which is the measure from a human eye or from like a telescope from Earth. And B and V filters are filters which are used in astronomy to improve contrast and make it easier to analyze like images like this by removing clutter from images. And they work by only allowing specific wavelengths of light to be observed. And so the B filter is a blue filter, and it only allows light of wavelengths 400 to 500 nanometers through. And the V filter is visual and allows light wavelengths 500 to 700 nanometers through. And these apparent magnitude measurements are all taken in relation to a reference star. As you can see below, this is the formula to get the magnitude of a star. And to get it, you need to know the magnitude of another star, which is a reference star. And we selected star 125 from Shinkarini's star numbering system as a reference star because we know its magnitude. And using its magnitude, we can calculate the magnitude of all the other stars in NGC 1245. So reddening is, or redshift, it's an astronomical phenomenon, and it happens to all astronomical data ever. And it's basically when light from a star interacts with interstellar particles, the wavelength of the light is stretched and the color is shifted towards the red end of the visible spectrum. And what this does is it basically just has all the observed light from space be a little redder than it actually is. And we can correct for this by calculating and determining a reddening value, which is like how much redder it gets, and subtracting it from its measured value to get its real value.
So this is our graph. On the x-axis, we have the color index, or the B minus V, and on the y-axis, we have the V values. And so underneath it, we also have the ZAMS line, or the zero-age main sequence line, which represents the time when stars initially enter the main sequence on the HR diagram. So what we are looking for is a cutoff star, because an open cluster can be no older than its youngest star. So we have to base off all our calculations off of the cutoff star, which we determined to be star 422. And so for our calculations, we have to find in absolute magnitude, and we can't tell that but based off of our data. So we have to find a star that has a very similar B minus V to our cutoff star and use that absolute magnitude. So we decided on the reference star of HIP 111.807 with an absolute magnitude of 2.13, and its cutoff star number is 422, and with the apparent magnitude of the cutoff star being 14.05. And so plugging it into the distance formula, we get 2,856.27 parsecs, which is equivalent to 9,311.46 light years. And so to determine the age of the open cluster, we have to use spectral class. And basically, it's based off of the stars B minus V values. We can sort them into the spectral class. And based off of that, we can find their age, color, size, and temperature. And for the purposes of our experiment, we wanted to find the ages. And our cutoff star, happened to be an A star. So based off of the fact that it's an A star, specifically an A5 star, we can determine that our globular, or our open cluster, is approximately 1 billion years old, and the distance from it is 9,311.46 light years.
So the first thing we learned is we learned exactly what open clusters were in astronomy. And the next thing, we learned how to use astronomical software like AstroImage-J. So Image-J, many of y'all will know, is extensively used biomedical software. And AstroImage-J was very useful in our project in finding photometry, like Michael discussed, of these stars in NGC 1245. Now, the third thing is we learned how to interpret large data sets. The 5 of us interpreted of over 400 stars, and we corrected for reddening. We graphed these scatter points, and yeah. Collaborated with like-minded students, and we also received the opportunity to work with an amazing professor. And Miss Cooper is a PhD student. She works at Caltech. She's also worked in high school, and she's an amazing mentor. And the last thing is we gained career experience. Many of us have sort of honed in our decision on whether or not we're going to pursue a career in astronomy, and NASA Seas has definitely helped us make that decision. Some of the challenges we had were, it was really unclear about these large groups of stars. These stars in our images were in groups, and many of them were very faint. And it was hard to distinguish between them. So these stars had such low magnitudes, and it really made us have a difficult time finding the magnitudes and to get sort of precision in that process. The second challenge is the virtual communication and collaboration. We did everything over Zoom. We did everything over text messages and phone calls. So of course, we had to deal with that. It wasn't in person. And the last thing is an interesting challenge. Our data was supposed to fit a certain line. It's called the main sequence line, zero age main sequence. But our scatter points didn't really line up with that line. And we had to do some adjusting to make sure that those scatter plots were on that zero age main sequence line. And once that was the case, our data was able to be interpreted.
To begin, working on this project gave me the opportunity to explore new topics in astronomy and the experience of collecting large amounts of data, which I have not done before. And especially, I'm super thankful to NASA Seas and our mentor, Ms. Cooper, for giving me this chance and also guiding me throughout our journey of our research.
Being given a chance to do this project has given me unequivocal inspiration and excitement to go into a career in astronomy, because I've loved to learn about the theory, but I've never actually gotten a chance to actually collect data and interpret it. And so that was an amazing experience. I'm so happy I got to do a project like this, and I can't be more grateful for Seas for the opportunity.
Yeah, I want to thank Seas and Ms. Cooper for this amazing experience. And I really loved doing all the actual like astronomical work that NASA does, like getting a taste of it. And I'm going to remember this going forward, and I hope I can do more in the future, because this was my first like actual experience in astronomical research.
Yeah, so Seas really helped me enhance my understanding and solidify my interest within space science. And I really had the grateful opportunity to engage in astronomy through the scientific lens, and am thankful for Seas for the experience that I've had over these past few weeks.
And like I say in this statement here, before I attended Seas, I had done a bunch of research in astronomy. I attended lectures, I'd taken images in my telescope and such, but I never had that true, authentic, and genuine research experiments with astronomy. And I will never forget how invaluable NASA Seas has been in providing me with such a strong foundation in astronomical research. So thank you so much, NASA Seas. And on behalf of all of us, we would like to thank NASA. We would like to thank the Texas Space Grant Consortium, the NASA Seas program, as well as the Center for Space Research Science in UT Austin. UT Austin was very kind to include us in this program. And of course, we'd like to thank our mentor, Mrs. Cooper. She's been an amazing mentor. And we'd also like to thank all the coordinators of the Seas program. Thank you so much.
Interesting research. So I want to invite the team to please turn on their cameras and to unmute their mics. We have several questions for your team. The first question is, how did you balance your scientific goals and also your group goals?
I can take this question. So in the beginning, we definitely had our initial goal of calculating the age and distance of our open cluster. And we kind of used that goal and split up into different parts. So for example, each of us had a different section of stars to calculate the magnitudes for. And at the end, once we all did our own individual research, we went on a call and kind of gathered our data together. So basically throughout the entire process, we've kind of been collecting data individually, but then working as a team together to accomplish our main goal of finding the age and distance.
Great. And are there other factors besides the known magnitude that determine the best choice of a reference star?
I can take this question. So not particularly. So to do the photometry on Astro Image J, we only needed to really have that known magnitude to be able to collect data for all the other members in the cluster. And since we had the magnitudes in both the filters for star 125, we were able to use that for reference.
What was the biggest challenge your group faced during your research?
I think I can take that question. The biggest challenge we faced was it was very hard at the very beginning to sort of detect these very faint and low magnitude stars. Like we said in the presentation, some of these stars have 18 magnitudes, and that is so faint that it's very hard. You got to turn the contrast up very high, and that introduces a lot of imprecision and inaccuracy in this project. But because we had so many data points, we had over 400 stars that we were taking the magnitudes of. It made it such that it was maybe a little easier if we did make some mistakes, that everything was sort of level out with so many data points.
And does the software determine the magnitude, or do you use your human eye to interpret those images?
I can take that. So what we did is we had a star where we knew the magnitude of that star. In our case, it was star 125. And so you click on that and you enter the magnitude for that. And any star you click after that, it will tell you the magnitude of that based off of the magnitude of the original star.
So what do you think was the most valuable thing in this particular project?
Well, I think that the most valuable thing in this project is we're really working as a team towards sort of finding the missing pieces in this large puzzle of stellar evolution. The main goal of this project is to sort of contribute to how these stars evolve, whether they're going to go down the main sequence to red giant to white dwarf path, or are they going to go from the main sequence to red giant to neutron star and the black hole path. All these sort of properties that we're determining the age of the star cluster, the distance of the star cluster, lead to identifying properties such as metallicity, to extinction, to distance, and to velocity of these stars. So there's many properties we're able to determine from this project, and it gives us a better understanding of how these stars are evolving and how open clusters in general function.
And yeah, just to add on, I feel like on more of the research side, kind of calculating and finding the magnitude, like Grace said, using Astro Image J definitely set the foundation for our entire research. And just like Rod just mentioned, using this data and with the research that we conducted, it's definitely very useful for astronomers and the area of stellar evolutions and just overall just finding new properties in space.
Sounds wonderful. And thank you for all that you contributed to the project. We enjoyed your presentation, and thank you for sharing your research today. So a meteorite is a solid piece of debris from an object, such as a comet, asteroid, meteoroid, that originates in outer space and survives as it passes through the atmosphere to reach the surface of a planet or moon. During their investigation, interns learned how NASA searches for meteorite samples and curates them. They investigated OSIRIS-REx and other asteroid missions. Thank you to Suzanne Foxworth with Jacobs Technology at NASA Johnson Space Center for her guidance and dedication. We have 4 team presentations followed by a Q&A. Our first team is the new prebiotic compounds found in the Murchison meteorite team.
I'm Shamika Agarwal.
I'm Shireen Agarwal.
I'm Ledin Hashi.
I'm Gabriella Milgram.
And I'm Parag Srinivasan.
And our project was on the new prebiotic compounds found in the Murchison meteorite. The Murchison meteorite fell near Murchison, Australia in 1969, and it's significant because it was collected soon after its fall, which meant that there was no contamination from Earth. So the amino acids and nuclear bases that were found were extraterrestrial, and it was a higher likelihood of it being so. We conducted our research by looking at multiple scholarly articles and scientific studies, and we came to the conclusion that there are over 100 prebiotic compounds in the meteorite. The composition of these compounds suggests that they were not formed in the conditions possible on Earth, and this provides a better understanding of the formation mechanisms of amino acids.
Our research focused on the Murchison meteorite, which fell in 1969 in Australia. This carbonaceous chondrite is significant in the field of astrobiology because inside the meteorite, scientists found two important prebiotic compounds: amino acids, the building blocks of proteins, and nucleobases, an essential component of nucleic acids like DNA. Some of these compounds have not previously been found on Earth, prompting questions about the possibility of extraterrestrial life and the origins of life on Earth.
From our research, we found 96 different amino acids and 8 purine nucleobases that have been identified by name in the Murchison meteorite. Glycine was the most abundant amino acid found, followed by alanine, hypoxanthine, isovaline, beta-alanine, and 2-amino isobutyric acid. As shown in our graph, guanine was the most common nucleobase, and it had the highest concentration with 72 parts per billion, and it was followed by xanthine, adenine, isoguanine, purine, and 2,6-diaminopurine. There have also been 6 new diamino acids recently found in the Murchison meteorite, making it the first time diamino acids were discovered in a meteorite. The 6 concentrations in the meteorite are listed in parts per billion.
All of the research we pulled data from used the same data set. This data set was created by isolating the amino acids within the Murchison meteorite and measuring their concentrations. What those researchers did is they took a core sample of that and then tried to remove the impurities mixed in by boiling it in water for 20 hours. Whatever was left over, the pure stuff, was powdered and then subjected to acid hydrolysis, which left behind the precipitate of impurities while the actual amino acids were dissolved. Further organic material was removed by dissolving it in diethyl ether and then removing that. The salts that formed from the acid reaction were taken out in an ion column. And then finally, the remaining amino acids were converted into isopropyl derivatives and subjected to gas spectroscopy, which differentiates them based on boiling point.
In conclusion, the molecular composition of the amino acids on the Murchison meteorite demonstrates that they are of extraterrestrial origin. Discovering an excess of left-handed amino acids on the Murchison meteorite also serves as evidence for the theory that amino acids delivered by asteroids or comets to the early Earth contributed to the origin of only left-handed base protein life. Comprehending the origins of life on Earth provides a new basis for the search for extraterrestrial life. The amino acids on the Murchison meteorite must have also used other formation mechanisms in addition to the Strucker reaction. Future studies may focus on how these amino acids formed or examine further into how meteorites may have carried prebiotic organic molecules to primitive Earth.
We would like to thank Margaret Beggio, Selena Miller, the NASA TSGC team, Suzanne Foxworth, and all the NASA ERAS speakers.
We'd also like to thank the SEAS program for the wonderful experience. We learned a lot. It truly taught us more about STEM, and now we're all more excited to go into STEM fields. And it also taught us more about teamwork and collaboration that can be used in many other applications as well. So thank you.
Great. Our next meteorite team is the team on limitations on the meteorite pairing process.
Hello, everyone. My name is Alex Gallardo, and today, along with my team composed of Wesley Deklich, Mark Revela, Alessandro Vendano, and Almates Barati, we'll be presenting the limitations on the meteorite pairing process. So meteorite pairing is a process of identifying the many fragmentations of a meteorite separated during atmospheric travel or upon collision with terrestrial land. The pairing process is accomplished with thorough comparison of properties such as petrochemical composition, mineral composition, cosmic ray exposure, as well as thermoluminescence levels. The pairing of meteorites is important to us because it allows us to understand the journey of a meteorite from its origin to its final destination, the terrestrial age of the meteorite, as well as the early formation of the solar system. Scientists have developed new forms of tackling the challenges of pairing. These include the use of genetic nomenclature algorithms, as well as the Bayesian classification system, which both automate and ease the challenges in the pairing process. This research covers in depth the many challenges scientists face when it comes to pairing located samples and the solutions to the many complications involved. Thank you very much.
Meteorite classification groups similar meteorites together. It evolves as the knowledge and data of meteorites expands. A variety of methods are used to classify meteorites, but the groupings based on these datasets are not always consistent with each other. A successful meteorite pairing is denoted by finding absolute similarities between two or more meteorite fragments in the properties tested, but a negative piece of evidence can make these similarities redundant.
One of the main difficulties of meteorite pairing is the lack of a clear set of guidelines. Scientists use a variety of analytical techniques to determine pairs, and yet some scientists might be able to pair a meteorite while others cannot. For example, Benoit considered the primary characteristics as shock rate, phaelite, and ferrosilicate content, while Bogdanovsky used mineralogic composition and textures of Dinvo to compare it with other primitive chondrites. A proposal for a global meteorite pairing system falls under three categories: physical characteristics, geographic proximity, and recent space history. Human error and inappropriate equipment can lead to failures when classifying meteorites. New advancements in image processing, deep learning, and computational techniques allow for automating this process. Artificial intelligence can scan meteorites and reduce the work of scientists when given an appropriate, generous dataset. Furthermore, even if a meteorite is paired, there is still uncertainty due to the lack of data. Elephant moraine 85721 was originally classified as a brecciated eukaryote by Paul Warren from UCLA, but it was later recognized to be a brecciated lunar volcanic rock. Scientists have added a generic algorithm that assigns a score to pairings.
The implementation of a global meteorite database could greatly improve access to samples and their analyses. By using drones equipped with light detection and ranging, or LiDAR systems, searching open areas such as Antarctica could be made far faster. Finally, AI analysis can compare thousands of meteorites at once and set an equal standard of probability for each pair.
And as we find out more about the limitations of the meteorite pairing process, there's a few things we can try to implement in order to make this easier for scientists. Firstly, we have artificial intelligence. So by using photomicrographs as well as other computational techniques, we can try to make this process quicker and a lot more automated for these scientists. There's also genetic algorithms, which are often compared to natural selection in the sense that pairings are put up against each other for competition and the best pairings come out on top. There's Bayesian classification, which uses statistics and probability in order to find correlation between variables, and this also leads to newer classifications such as the Bayesian belief networks. We have the scoring system that was previously mentioned, in which pairings are assigned a letter depending on how strong they are, and there's also technology that can be used outside of the lab in the field, such as in Antarctica or in deserts, in order to find these meteorites quicker, such as drones. And again, the purpose of this is to not make this process fully automated, but to try to make it a lot easier for scientists.
My team and I gained a lot of good experience from our time at SEAS. One of the best features of the program is how each intern is taught how to conduct research and find scientific papers which are suitable sources. On the other hand, a challenge the group ran into was the team dynamics and coordination. Learning to communicate effectively was key.
The STEM enhancements in our science program allowed us to explore topics not offered in traditional high schools. It was very exciting to collaborate with talented students and mentors from all around the United States. Not to mention, it sparked new interests in astronomy, earth science, and interdisciplinary research, and also solidified future career interests in science, math, and engineering.
Thank you to mentor Susan Foxworth, as well as everyone else who organized and ran the SEAS internship. So Selena Miller, Margaret Baggio, and the NASA Texas Space Grant. And thank you to all of the NASA era speakers who gave presentations throughout the internship.
Our next meteorite team is Meteorites as Messengers of Life.
Hello everyone, welcome to the SEAS presentation 2022. My name is Mamadou Ba. To introduce our project, we work as a group to answer the question, how could meteorite have carried life to habitable planets? So I'm going to talk about the abstract. Carbonous contains a large amount of organic molecule, amino acid, and even water. Determining how meteorite could have carried life to habitable planet is important for understanding theories about extraterrestrial and terrestrial life. The research was conducted through reading online scientific studies and various scientific articles about meteorites and their specific composition. The fact that meteorites likely did bring organic molecules to Earth may explain why life formed here. This serves as a case study to refine technique and environments, allowing the detection of potential habitat and possible life on other planets.
Hello, my name is Luke Chung, and I'll be doing our intro. Panspermia is the theory that life originated in space and is carried to planets via meteorites and comets. And this is very similar to the theory of pseudopanspermia. The only difference is that pseudopanspermia refers to the ingredients of life, so amino acids, rather than living organisms. Meteorites have been confirmed to contain amino acids, and this includes the Murchison meteorite and the Nakhla and Tagish Lake meteorites as well. Scientists have searched for the existence of peptides and proteins in meteorites, and our project focuses on the validity of pseudopanspermia through research on similarities between terrestrial amino acids and amino acids in meteorites.
Hi, my name is Melanie Aguirre, and I'm going to be presenting the results. Amino acids are a basic building block of life. Carbonaceous meteorites, such as the Tagish Lake and the Murchison meteorite, contain several forms of amino acids. Today, about 96 amino acids have been named in meteorites. The majority of these amino acids are left-handed amino acids. Scientists have yet to discover why amino acids take the left-handedness form, but they believe it is a result of how they form in space. Apart from finding amino acids in meteorites, scientists have also found protein. This protein is referred to as a hemolithin, found in aquifer 086. This protein was formed by glycine, the simplest form of amino acid, which plays an important role in all terrestrial life, bound to iron, oxygen, and lithium atoms. This protein also formed in space, specifically in the protoplanetary disk, over 4.6 billion years ago. The discovery of amino acids and complex structures of protein has continued to lead scientists to speculate that the origin of life on Earth is directly tied to the arrival of such meteorites on our planet.
Hello, my name is Ryan Fang. This is a graph I compiled using data from the Murchison meteorite. As you can see, out of all of the organic molecules found on the meteorite, 8.3% were amino acids. And of these amino acids, there were 80 different unique ones just found on this one meteorite.
For our recommendations, we believe that efforts should be made to see if water and amino acids are usually found on the same meteorite, because this may strengthen the panspermia theory. Efforts to discover peptides and proteins in meteorites should be continued, and more research should be done to discover why amino acids take on a left-handed form. Scientists should also continue to research how exactly amino acids formed in space and arrived to Earth, contributing to the creation of terrestrial life. Future research will not only help scientists uncover the origins of terrestrial life, but also answer questions about other potential life as well.
So in conclusion, the existence of amino acids and other organic molecules on meteorites suggests the panspermia theory. Out of the large group of amino acids found on meteorites, the vast majority of these are left-handed in structure, which correlates with most organic amino acids, which are also left-handed. This possible connection could lead to a better understanding of life here on Earth and potentially extraterrestrial life. So we all enjoyed this program, from the speakers to the learning. I particularly enjoyed the research environment, and I'm sure my fellow interns would agree that this will prepare us for our future careers in STEM.
We would like to thank Margaret Baggio and Selena Miller, the NASA Texas Space Grant Consortium, Ms. Suzanne Foxworth, and all the NASA Aries and NASA Seas speakers. Thank you so much. And here's our poster. Does anyone have any questions?
We have one more presentation in the meteorite team before we do the Q&A. And next up is the pre-solar grains, a window through space and time team.
Hello.
We are part of the SEAS 2022 meteorite team, and our project is titled Pre-Solar Grains, a Window Through Space and Time. Following their formation in stars, heavy elements were scattered throughout the universe via supernovae and stellar winds. Heavy elements that were present during the formation of the solar system have been preserved as pre-solar grains in primitive meteorites. Identified by their anomalous isotopic composition, pre-solar grains stand out from other matter found naturally throughout the solar system. Isotopes found in these grains have been preserved since the solar system first formed, and therefore vary from uniform isotopes of the present. Because studying pre-solar grains essentially enables scientists to look at distant stars through a microscope rather than a telescope, many significant conclusions can be drawn from them.
Pre-solar grains are microscopic particles that were condensed during the formation and collapse of stars. These grains come in many different types. Diamond, silicon carbide, graphite, and oxides are the most common. Pre-solar grains are found all throughout chondritic meteorites. However, they're most commonly analyzed when found within the chondrules and refractory inclusions. Scientists analyze many different aspects of these grains, most commonly the isotopic compositions. The anomalous compositions found in pre-solar grains help to identify the meteorite's origin, give evidence towards an isotopically heterogeneous pre-solar nebula, and detail nucleosynthesis.
We gathered lots of information to make this project possible, but these are just some facts we found interesting during our research. With the size and the unique properties of the pre-solar grains, it's hard to identify them just by their looks. Only about 5% of meteorites found on Earth have traces of pre-solar grains. Scientists can locate pre-solar grains through the unique isotopic ratios on the chondrites of a meteorite. These 4.7 billion-year-old grains need special equipment to be able to carefully examine them. The instruments include secondary ion mass spectrometry, scanning electron microscope, transmission electron microscope. NanoSIMS is the main device used because it specializes in isotopic ratios along with other qualities.
The pre-solar grain field of study is providing optimistic results for the field of astrophysics. Further research promises a greater understanding of stars' evolution, both stellar and nuclear synthesis. Nuclear synthesis being the production of chemical elements from simple nuclei, commonly in stars. It similarly aids scientists' understanding of meteorites' origin based on the composition of those pre-solar grains and forms, more accurate stellar formation and evolution models. An improvement on the process to study individual grains is needed because of the difficulty to analyze smaller grains. Studying singular grains provide more information on the individual stellar formation since the origin of all pre-solar grains heavily varies.
Because of their distant formation and preservation, pre-solar grains contain valuable information. First of all, examining the isotopic composition of the grains tells scientists the type of stars from which they came and can teach them about processes that occur within these stars, such as nucleosynthesis, mixing that occurs during supernovae, and the star's galactic history. Furthermore, pre-solar grains are strong evidence towards the heterogeneity of the solar nebula.
Both of these graphs show the isotopic compositions of pre-solar grains, focusing on nitrogen and carbon. The right graph shows a wide range of grain types. The significance of this graph is that it shows the anomalous isotopes such as carbon-13 and nitrogen-15 are much more prevalent in the pre-solar grains than typically throughout the solar system. These solar lines show the isotopic ratios of most matter throughout the solar system. So the immense amount of data under these lines represents the prevalence of isotopic anomalies. The left graph with pre-solar grains from the Hingzhen meteorite have mainly type X1 grains, which are not anomalous in their carbon compositions. This corresponds to the X1 grains in the right graph. These X1 grains, though, show an immense abnormality in their nitrogen isotopic compositions.
Our team reflected on our experience here at the SEAS internship. We all agreed this was a unique experience and we learned skills that will stick with us for our future careers.
The whole team says thank you to all sponsors of this program, including our mentor, Ms. Foxworth. Are there any questions?
Thank you for your research. So these were 4 great presentations from the meteorite teams. And if I could get you to please turn on your cameras and unmute your mics. We have the first question is for team number 1. How different is the Murchison meteorite from other meteorites found on Earth?
So I can take this one. The Murchison meteorite is a carbonaceous chondrite, so it's like one of the most primitive types of meteorites. And actually only 4.6 of meteorites that fall to Earth actually fall into this category. And the Murchison meteorite is especially special because it was collected soon after its fall, so it avoided terrestrial contamination.
And another question for team number 1. What was the most surprising thing you discovered during your research?
We were surprised by how evolved the amino acids were. The fact that there were proper amino acids within the Murchison meteorite at all, but also how evolved and how close to producing life they were, made us surprised because we couldn't imagine that something would form like that out of their base materials.
And for team number 2, what is a photomicrograph?
So a photomicrograph is a photograph of just a microscopic object taken with the aid of a microscope. So again, we're not trying to make this process fully automated, but by being able to take these pictures and combining it with the AI, we can use at least physical features in order to make the pairing process a lot more quicker and easier for the scientist.
And also for group number 2, is there a central meteorite database that scientists use for pairing?
Yeah, actually there is. I can take this one. There's a meteorite database by the Lunar and Planetary Institute that belongs to the Natural History Museum, and it's actually frequently updated with new meteorites. And as of now, I think there's around 70,000 meteorites in the database that include images and names of almost all the meteorites ever found. And this is actually really significant because it improves the quality of meteorite pairing and reduces the work of scientists, as this computer can narrow down all possible pairings.
And team number 3, are carbonaceous chondrites the only meteorite that has organic molecules?
Actually, carbonaceous chondrites are not the only type of meteorite that can contain these organic molecules, but they're more preferable over other types because they have they are out of carbon. They're carbon based, and they also have an abundance of organic molecules. And we can see this in the example of the Murchison meteorite that had over 80 types of amino acids.
And also for team number 3, has your research changed how you think about how life formed on Earth?
I can take this one. So yeah, like questions about life are probably some of the most important questions, both in science and in metaphysics. Personally, I had never thought about the prospect of life developing somewhere other than Earth while researching this project. So panspermia, if true, could suggest that, we are not the only life, and it could also, tell us important things about us as humans.
And for team number 4, how long have scientists been studying pre-solar grains?
So the first really detected source of pre-solar grains on Earth occurred in around 1960, but it wasn't for another few years that scientists actually identified the source as pre-solar grains. They were kind of confused by it.
And also for team number 4, why do the X1 grains show abnormalities?
Unlike the other grains, like the mainstream and type Y grains, X1 grains formed from supernovae instead of in AGB stars.
Great. Well, you've all done a wonderful job with your research, and we appreciate you sharing your results with us today. The success of the NASA STEM Enhancement in Earth Science program is determined not only by the commitment from the students and their research, but also by the mentors and project assistants. Your passion for youth development, STEM learning, and NASA missions and opportunities is to be applauded. Selena and I want to thank you for your time and your talent that you shared with our student interns. And I know the C's interns appreciate your guidance and advice as they conducted their research. So we want to thank you for joining us for day 2 of the NASA C's Science Symposium. Please join us tomorrow at 12:30 Central Time as we continue to share the amazing research and results from the 2022 NASA C's internship. Enjoy your